Imagine a world where the largest animals that ever walked the earth were not merely enormous, lumbering beasts driven by instinct and hunger. Imagine that when the first Tyrannosaurus rex placed its enormous foot upon the Cretaceous Earth, somewhere in what would one day become the Badlands of Montana, it did so not as a creature of pure reflex and ancient appetite, but as an animal with memory, with recognition, with something that might, if we are generous with our definitions, be called thought. Imagine that when a herd of Parasaurolophus moved across the floodplains of ancient North America, the haunting, resonant calls drifting from their hollow crests were not random noise. They were language. Not language the way we understand it, layered and complex and abstract, but something older and perhaps more honest. Communication built from feeling and experience and need, passed between individuals who knew each other, who remembered the past, who anticipated what might come. Imagine that somewhere deep in the Cretaceous forests, a small group of troodons, those bird-hipped, large-brained theropods with forward-facing eyes and grasping hands, were doing something that we would, if we could somehow observe them across the distance of 66 million years, recognize as problem-solving, as learning, as teaching. This is not science fiction. This is science. Or rather, it is the frontier of science, that uncertain, thrilling borderland where what we thought we knew about the ancient world begins to dissolve like morning mist, and something stranger and more wonderful takes its place. We have spent the better part of 2 centuries thinking about dinosaurs in a very particular way. We imagine them as evolutionary dead ends, spectacular in their size and variety, but ultimately failures. Animals too slow, too cold, too stupid to compete with the warm-blooded mammals that would eventually inherit the Earth after the asteroid at Chicxulub broke there, ending 66 million years ago. We put them in our museums as monuments to excess. We made them into monsters in our films. We taught our children about them as cautionary tales of extinction, great beasts brought low by their own limitations and a rock from space. But science does not stand still, and the science of paleontology has, in the last several decades, been undergoing a revolution so profound, so disorienting in its implications, that many of the old ideas about dinosaurs have had to be abandoned entirely. We are learning that dinosaurs were not cold-blooded. Many were warm-blooded, or something more nuanced and interesting than either of those categories quite captures. We are learning that many carried feathers, not just the lineages that became birds, but many of the great theropod predators, including probably some species of Tyrannosaurus rex. We are learning that they were social in ways we never imagined, that they cared for their young, that they communicated in sophisticated ways, that their brains were in many cases far more developed than we ever suspected. We are learning, in short, that the mental picture of dinosaurs that most of us carry around is badly outdated, that the creatures who ruled this planet for 165 million years were not the slow, swamp-dwelling, reptile-brained failures of old imagination, but something far more nuanced, far more capable, far more interesting. And some scientists have begun to ask a question that once would have seemed too wild to take seriously. A question that, once asked, is very difficult to set aside. What if dinosaurs were more advanced than we think? Not just slightly more advanced, not just a little smarter than we give them credit for, but genuinely, startlingly, paradigm-shiftingly more advanced. What if, within the enormous breadth of dinosaur diversity across 165 million years of evolution, there were lineages pushing in directions that, had they been given more time, had that asteroid not arrived precisely when it did, might have led somewhere we can barely imagine? Tonight, we are going to follow that question wherever it leads. We are going to look at what the science actually says about dinosaur intelligence, about their social behavior, about their biology, about the structure of their brains, and the capabilities of their senses. And then we are going to ask, carefully and with appropriate wonder, what all of that might mean. This is a story about ancient animals, but it is also, in its way, a story about intelligence itself, about what it means to think, to feel, to communicate, to learn, about how those capacities arise, how they evolve and what they might become. Let the question settle over you as you breathe slowly and deeply. Close your eyes, if you haven't already. Let the world outside this moment recede. We want to thank you for supporting us, and it would mean so much if you could support the channel by leaving a like and subscribing to help us keep this channel going. Anyways, back to the video. Something extraordinary happened on this planet long before we arrived. Something that we're only now beginning to understand. And understanding it changes not only how we see the past, but how we see ourselves. If you enjoy listening to sleepy prehistoric dinosaur stories like this, subscribe. I post stories like this weekly. Let's begin. To understand how advanced dinosaurs might have been, we first need to understand something that scientists spent much of the 20th century getting catastrophically wrong. For most of the history of paleontology, from its beginnings in the early 19th century through much of the 20th, dinosaurs were assumed to be cold-blooded, ectothermic, to use the scientific term. Like modern lizards and crocodilians, they were thought to depend on their environment for body heat, basking in the sun to warm up, slowing down in cold weather, incapable of sustained activity the way a warm-blooded mammal can sustain it. This assumption was not arbitrary. It seemed to follow logically from the evidence available. Dinosaurs were reptiles, and reptiles were cold-blooded. The math seemed simple, and cold-blooded animals by their nature have limited metabolisms, limited capacity for sustained effort, limited neural complexity. A cold-blooded brain ticks along slowly, processes information at a lower rate, requires less oxygen, less fuel. If dinosaurs were cold-blooded, they could not have been very smart. Their brains would not have needed to be, and their bodies could not have supported the metabolic cost of significant neural complexity. Case closed, or so it seemed. Then, in 1969, a paleontologist named Robert Bakker gave a talk at a conference in Washington, D.C. that would set off what has since been called the dinosaur renaissance. Bakker argued with passion and with evidence that the assumption of cold-bloodedness was almost certainly wrong. He pointed to the posture of dinosaurs, upright, active, dynamic, and argued that only warm-blooded animals could have sustained the kind of activity their skeletons implied. He pointed to the bone structure of dinosaurs, which in many species showed the rapid, sustained growth patterns characteristic of warm-blooded animals rather than the slow, seasonal growth of cold-blooded ones. He pointed to their evolutionary descendants, the birds, undeniably warm-blooded, undeniably descended from theropod dinosaurs, and asked why we should assume the change had been so abrupt. It took decades for the scientific community to come around. The evidence accumulated slowly but inexorably. Isotopic studies of dinosaur teeth and bones revealed body temperatures consistent with warm-blooded animals. Studies of bone microstructure showed the fibrolamellar bone typical of endotherms, animals that generate their own body heat internally. Analysis of growth rates showed that many dinosaurs grew fast, sustained, year-round, not the slow seasonal growth of reptiles. But the picture that emerged was not simply that dinosaurs were warm-blooded in the way mammals and birds are warm-blooded. It was more interesting than that. Many dinosaurs appear to have occupied a metabolic middle ground. They generated their own body heat, but they did so somewhat differently than modern mammals. Some researchers have proposed the term mesothermy, a metabolism intermediate between the cold-blooded ectothermy of reptiles and the full endothermy of mammals and birds. Mesothermic animals can be active across a range of temperatures, can sustain effort that would exhaust a cold-blooded animal, but do not spend the enormous caloric energy that full endothermy requires. Think of it this way: a crocodile, cold-blooded, needs to eat only about twice a month to sustain itself. A mammal of similar size might need to eat every day, or every few days. The warm-bloodedness that makes mammals so active and capable is also extraordinarily expensive. Mesothermic dinosaurs may have enjoyed a kind of metabolic efficiency that was, in some ways, superior to either extreme. Active enough to be dynamic predators and complex social animals, efficient enough not to require the relentless caloric input that full endothermy demands. This metabolic middle ground has profound implications for what dinosaurs could have been capable of. A warmer, more active metabolism supports a more complex nervous system. It supports faster information processing, greater behavioral flexibility, more sophisticated responses to novel situations. It supports, in short, more intelligence. And the brain evidence supports this picture. Early studies of dinosaur brain size were limited to what could be inferred from the shape of skull cavities, endocasts essentially, where the inner surface of the skull preserves a rough impression of the brain's outer surface. These early studies tended to show small brains relative to body size and were taken as confirmation of the old cold-blooded, dim-witted image. But more sophisticated analysis has revised this picture dramatically. When researchers compare dinosaur brain sizes to their expected body masses using modern statistical methods, many species show encephalization quotients, the ratio of actual brain mass to expected brain mass for an animal of that size, that are considerably higher than previously thought. Some theropod dinosaurs, particularly the small to mid-sized ones like Troodon, Velociraptor, and their relatives, show brain-to-body ratios approaching, or in some cases comparable to modern birds. And modern birds, as we have learned in recent decades, are not the feathered automatons we once assumed. They are cognitively complex, socially sophisticated, capable of remarkable feats of memory, learning, and problem-solving. Crows use tools, parrots understand concepts of number, and can learn hundreds of words with apparent comprehension of their meanings. Ravens plan for the future. Pigeons can recognize individual human faces. The bird-brained insult has become deeply ironic as science has revealed just how capable avian cognition is. If the small theropod dinosaurs had brains comparable in relative size to modern birds, what might they have been capable of? Here is where we have to be careful. Brain size is not the same as intelligence. The structure and organization of neural tissue matters enormously, and we cannot directly observe the internal organization of brains that have been gone for 66 million years. A brain that is large relative to body size might be devoted primarily to enhanced sensory processing, rather than to what we would recognize as higher cognition. We cannot know for certain. But we can draw tentative inferences. And the tentative inferences are striking. Consider the cerebellum, the region of the brain, involved in coordination and the processing of learned motor sequences. In many theropod dinosaurs, the endocasts show a well-developed cerebellum, suggesting refined motor control, the ability to execute complex, learned movement patterns. This is what you would expect in an animal that needs to coordinate sophisticated hunting behavior, navigate complex environments, or engage in elaborate social displays. Consider the olfactory bulbs, the brain regions processing smell. In many dinosaurs, these are large, suggesting a rich sensory world built around olfactory information. But in many theropods, the visual processing regions also appear substantial, consistent with the large, forward-facing eyes of animals like Troodon that suggest predators with binocular vision and depth perception. And consider above all what warm-bloodedness and elevated brain complexity imply for behavior. Warm-blooded animals with complex brains do not simply react to their environment. They model it. They anticipate it. They remember it. They learn from experience and modify their behavior accordingly. They play, especially as juveniles. And play is not a luxury or an accident. It is the neural machinery of learning running at full capacity, exploring possibilities, building the mental models that will guide future behavior. Did dinosaur juveniles play? We cannot know directly. But the behavioral evidence from related lineages, modern birds and crocodilians, the living descendants of the archosaur lineage that produced dinosaurs, strongly suggest that complex socially embedded behavioral development was possible, perhaps even common, in dinosaurs. Crocodilians, which most people assume are behavioral automatons, actually show complex parental care, learn from experience, and in captivity demonstrate clear individual personalities and the ability to solve novel problems. Birds, descended from dinosaurs, show all of this and far more. The picture that emerges, when you pull all of this evidence together, is not of dinosaurs as cold, slow, stupid reptiles. It is of dinosaurs as warm, active, behaviorally complex animals, in which evolution had been at work for 165 million years, building and refining the neural hardware of behavior in ways we are only beginning to appreciate. And in some lineages it had built something quite remarkable. Let yourself breathe that in. The ancient world was not a simpler place than ours. It was different. It was strange and vast and wild. But the animals that moved through it were not simple. They were alive in every sense, warm and active and present in their world. Rest with that image for a moment. The warm breath of a predator, the rumble of a herd on the move, the glint of an eye that sees and knows. We are only beginning to understand what was behind that eye. There is a place in the Badlands of Montana called Egg Mountain, And what was found there, beginning in the late 1970s, fundamentally changed the way scientists understand the inner lives of dinosaurs. The paleontologist Jack Horner was working a dig site near Choteau, Montana, when local people began bringing him fossils from a particular area, fragments of eggshell, baby bones, things they had been finding for years without quite knowing what they had. Horner followed the leads, and what he uncovered at what would become known as Egg Mountain was, at the time, nothing short of astonishing. Nests, dozens of them, circular depressions in ancient mudstone, each one carefully constructed, each one containing the fossilized remains of eggs, and in many cases the tiny bones of dinosaur young. The dinosaur was a species called Maiasaura, a name that Horner himself coined, which translates from Latin as good mother lizard, and the name was chosen deliberately because what the nests at Egg Mountain revealed about the behaviour of Maiasaura was exactly that, evidence of active, sustained parental care. The babies found in the nests were not hatchlings ready to leave. Their bones were not yet fully formed. Their teeth showed wear patterns consistent with having been fed, with having received chewed or processed plant material rather than foraging for themselves. And the nests were not isolated. They were spaced roughly the length of an adult Maiasaura apart, just far enough for the adults to move around the nest without disturbing the neighbours. They were a nesting colony, a community. This was not what cold-blooded, dim-witted reptiles did. Crocodilians guard their nests, but they do not typically feed their young. Most reptiles do not care for their offspring at all after hatching. What Maiasaura appeared to be doing at Egg Mountain was more like what birds do, more like what mammals do. It was parental investment in the truest sense. Sustained, active care of dependent young over an extended developmental period, and Maiasaura was not unusual. Since Egg Mountain, evidence of parental care in dinosaurs has accumulated from multiple species across the dinosaur family tree. Oviraptors, those feathered, beaked theropods long wrongly accused of nest raiding, are now known from beautifully preserved fossils to have brooded their eggs in exactly the posture a modern bird uses, settled over the clutch, with the eggs arranged in a ring and the parent's weight distributed to avoid crushing them. Several such fossils have been found, each one a frozen moment of devotion 66 million years old. Titanosaur sauropod nesting sites in Argentina have revealed nesting colonies that, like Egg Mountain, show consistent nest spacing and evidence of organised, coordinated egg-laying. These were not solitary animals leaving their eggs to hatch unattended. These were social animals, with a social dimension to their reproductive lives. The implications extend far beyond the nest. Parental care is not just a behaviour, it is a developmental system, a way of transmitting knowledge, skill, and social structure from one generation to the next. Animals that receive parental care do not simply survive to reproduce. They learn from their parents, they acquire behavioural repertoires that could not be assembled from scratch by any individual. They are socialised into the group, taught what to fear and what to seek, shown how to navigate the physical and social world. Consider what a young Maiasaura growing up in a nesting colony would learn. It would learn to recognise its parents and siblings individually. It would learn the sounds and behaviours of its species, the alarm calls that signalled danger, the contact calls that maintained group cohesion, the vocalisations of dominance and submission that structured social relationships. It would learn the landscape of its home range, the location of food and water and shelter, the patterns of seasonal movement. All of this would be transmitted not through genes but through experience, through social learning, through the slow accumulation of knowledge that characterises cognitively complex animals. And Maiasaura was a hadrosaur, a duck-billed dinosaur. One of the most social and, we are increasingly certain, one of the most cognitively sophisticated of the large herbivorous dinosaurs. Evidence from multiple hadrosaur species suggests they lived in large, organised herds that were not simply aggregations of individuals but structured social groups with internal dynamics. Dominant and subordinate animals, established relationships, perhaps something like hierarchy. The hollow crests that distinguished many hadrosaur species, most famously the spectacular tube-like crest of Parasaurolophus, were, as we will explore in more detail shortly, instruments of communication, of a sophistication and richness that implies a social life far more complex than we once imagined. But the social complexity of dinosaurs was not limited to the large herbivores. The predators show, it too, and the evidence from the predators is in some ways even more striking. Deinonychus, the inspiration for the velociraptors of Jurassic Park, though rather larger and more feathered than the film's version, was found in a particular pattern that suggested something remarkable. At several dig sites in Montana, the bones of multiple Deinonychus individuals were found, alongside the bones of large prey animals, specifically the ceratopsian dinosaur Tenontosaurus, and the pattern of the bones suggested that these Deinonychus had died in the process of hunting prey far larger than any individual could have taken alone. The inference was tantalizing. Had these animals been hunting cooperatively? Had a pack of Deinonychus, coordinating their movements in ways that only a socially intelligent animal could manage, brought down prey that would have been impossible for a lone individual? Cooperative hunting is one of the most cognitively demanding behaviors in the animal kingdom. It requires individuals to represent the intentions and actions of others, to coordinate with them in real time, to adjust their own behavior based on what their partners are doing. It requires, in short, a kind of social intelligence, the ability to model other minds. That is the hallmark of cognitively sophisticated animals. Wolves hunt cooperatively. Orcas hunt cooperatively. Chimpanzees hunt cooperatively. Ravens have been observed apparently coordinating with wolves. These are animals with substantial neural complexity, substantial social sophistication. If Deinonychus hunted cooperatively, it was doing something cognitively comparable to all of these. The evidence for cooperative hunting in Deinonychus is not conclusive. Taphonomy, the study of how organisms become fossils, is complex enough that multiple individuals dying near the same prey animal could reflect something other than a coordinated hunt. They might have died sequentially, individual scavengers, attracted to a carcass. They might have been competing rather than cooperating. The evidence is suggestive, not definitive, but it is not isolated. The discovery in China of several small theropods apparently fossilized in social groupings, multiple individuals of the same species in close proximity, in postures suggesting association rather than coincidence, adds to the picture. Trackways preserving the footprints of multiple large theropods moving in apparent coordination have been found in several locations. The evidence, though not definitive in any single instance, is cumulative, and there is this. Modern birds, the living descendants of theropod dinosaurs, are among the most socially sophisticated animals on Earth. The social complexity of corvids, crows, ravens, jays, is well documented and remarkable. Ravens track social relationships among dozens of individuals, remember specific animals they have not seen for years, form long-term coalitions and alliances, play elaborate social games. Harris's hawks hunt cooperatively in organized packs. Many bird species maintain complex hierarchies, engage in coalition politics, and show evidence of what researchers call theory of mind, the ability to attribute mental states to others. If modern birds are this sophisticated, if theropod dinosaurs were the evolutionary ancestors of birds, then the question of what the cognitive lives of those dinosaurs were like becomes considerably more interesting. Not because we can simply extrapolate backward from living birds to ancient theropods. Evolution does not work in reverse, and the specific cognitive abilities of modern birds evolved in specific ecological and evolutionary contexts. But because the demonstration that birds can achieve such sophisticated cognition tells us something about what the Archosaur lineage was capable of producing. The capacity was there. Evolution found it eventually in the lineages that became birds, in the larger theropods that went extinct 66 million years ago. It seems likely that evolution was moving in a similar direction, building similar capabilities in different bodies, different ecologies, different social contexts. What did those social groups look like? What did it feel like to move through one? Imagine a herd of hadrosaurs at dusk moving toward a river they have visited dozens of times before. The adults know this landscape in intimate detail, every fold of the ground, every patch of dense vegetation that might conceal a predator, every route to water. The juveniles press close to familiar adults, learning the route not from maps but from following. Calls drift through the warm Cretaceous air, low, resonant, the liquid tones of hollow crests processing the evening atmosphere into sound. In the tree line at the edge of the floodplain something moves. An adult at the front of the herd catches it. A subtle change in the air, a flicker of motion at the threshold of vision. A call goes up. Different from the contact calls, different from the low rumbles of the moving herd, it cuts through the warm air like a blade, and the herd responds. Not with chaos, not with random flight, but with coordinated movement, a closing of ranks around the young, a turning of the most experienced adults toward the threat, the herd becoming something larger and more capable than any individual within it. This is what social complexity means, made real in the ancient world. This is what it looks like when intelligence is not a single brain in a single skull, but a network of minds, each contributing, each receiving, each enriched by the others. And this, the science increasingly tells us, was the world that dinosaurs actually inhabited. There is a museum in Beijing that contains some of the most important fossils ever discovered. They came from a place called the Yixian Formation, in the Liaoning province of northeastern China, a geological deposit laid down roughly 125 million years ago in what was then a landscape of lakes, forests, and active volcanoes. When the volcanoes erupted, they sometimes released clouds of toxic gas that killed everything in the surrounding area: birds, small mammals, insects, plants, and, most relevantly, dinosaurs. And the bodies of those animals, falling into the fine-grained sediment at the bottoms of the lakes, were sometimes preserved with a fidelity that scientists of a century ago would have considered impossible. Not just bones, feathers. The Yixian Formation began yielding its secrets in the 1990s, and what it revealed upended the popular image of dinosaurs so completely that paleontologists have spent the intervening decades working through the implications. The small theropod dinosaurs of the Yixian were covered, many of them completely covered, in structures that range from simple, hair-like filaments to complex branched structures essentially identical to the feathers of modern birds. This was not entirely unexpected to specialists. The evolutionary relationship between birds and theropod dinosaurs had been established with considerable confidence since the 1970s, following the work of John Ostrom on Deinonychus and the renewed analysis of Archaeopteryx. If birds descended from theropods, and birds have feathers, then at some point in the theropod lineage, feathers must have evolved. What was unexpected was how widespread the evidence turned out to be. Not just the immediate bird ancestors had feathers, not just the small bird-like dromaeosaurids. The Yixian and subsequent discoveries from China and elsewhere showed feathers on tyrannosaurid relatives, small early members of the T-Rex family, on ornithomimosaurs, on oviraptors, on multiple lineages across the theropod family tree. And there are now strong suggestions that even the iconic giants, the large, famous theropods we have put in museums and films, may have had feathers in some form. Eutyrannus, a tyrannosaurid from China closely related to T-Rex, was found with unmistakable evidence of filamentous feather-like structures covering its body. Eutyrannus was not a small animal. It was a substantial predator, perhaps 9 meters long, but it was clearly feathered. What does feathered mean for our understanding of the inner life and cognitive complexity of these animals? More than you might immediately think. Feathers are not just insulation, though they are excellent insulation. They are the primary instrument of visual communication in modern birds. The specific arrangement, colour and structure of feathers conveys a wealth of information about the individual, its species, its sex, its age, its health, its reproductive status. The elaborate plumage of peacocks, birds of paradise, and lyrebirds represents an extreme expression of something present to varying degrees in virtually every bird species. The use of feathers as a communication medium. If the small theropod, dinosaurs of the Yixian, had feathers, and if those feathers showed the kind of colour and pattern variation we now know was present from melansosome analysis, then they were using feathers the way modern birds use feathers, as signals, as advertisements, as the medium through which social information was transmitted visually. This means they were reading those signals, distinguishing patterns, interpreting colour variations, associating specific visual signatures with specific individuals or with categories of individual. This requires a visual system of considerable acuity and a neural system capable of discriminating fine differences in visual stimuli and extracting their social meaning. It means, in other words, a richer social cognition than simple, reactive animals need. It means a world of individual recognition, status display, mate assessment, and competitive signaling. A social world that rewards cognitive sophistication. There is more. The evolution of feathers is a story, not just about insulation and display, but about the evolution of flight. The specific, intricately branched structure of flight feathers, with their precisely interlocked barbs and barbules, their asymmetric shape that generates aerodynamic lift, represents a level of developmental biological complexity that is remarkable. This complexity evolved in the theropod lineage through a series of stages that we can now trace with considerable precision through the fossil record. The earliest feather-like structures in the lineage were simple, unbranched filaments, sometimes called proto-feathers, that provided insulation. These evolved into simple branch structures, then into more complex ones, gradually approaching the structure of modern flight feathers. This progression is preserved in multiple fossil species from China, documenting the evolutionary history of feather structure with a clarity that was unimaginable 30 years ago. Each stage of feather evolution carried consequences for behavior. More complex feathers enabled more precise visual signaling. More complex feathers enabled more sophisticated aerodynamics. First, perhaps for balance and display, then for gliding, then eventually for powered flight. And each increase in behavioral and ecological complexity placed new demands on cognition, new selection pressures for behavioral flexibility and learning capacity. The animals of the Yixian Formation lived in a complex, ecologically diverse world. The same ash-covered lake beds that preserved their feathered remains also preserved the remains of the insects they ate, the plants that structured their habitats, the aquatic organisms of the lake ecosystems. It was a world of considerable ecological richness, and the theropods moving through it were doing so with warm blood, feathered bodies, excellent colour vision, and social lives structured by elaborate feather display. These were not simple animals, they were complex ones, navigating a complex world with cognitive tools that were, for their time and place, genuinely sophisticated. And some of them were small. Some of the most cognitively promising of the Yixian theropods were creatures that could sit comfortably in a human's hands. Quick, bright-eyed, active animals whose descendants would, in the fullness of time, become the birds. The transition to birds was not a sudden transformation. It was the continuation of a process that had been underway for tens of millions of years. The birds are not a new thing that emerged from the dinosaurs. The birds are dinosaurs, the surviving expression of a lineage that had been building toward exactly this kind of active, cognitively complex feathered existence for a very long time. When you watch a small bird moving through the branches of a tree, quick, alert, responsive, processing its world with evident intelligence, you're watching something ancient. Something that was doing this in a world of very different plants and predators 125 million years ago. The quickness is old. The alertness is old. The bright, attentive eye is old. This is what the Yixian tells us. Not just that dinosaurs had feathers, but that the dinosaur world was, in certain important ways, very much like the bird world, alive with display and communication, and the continuous social negotiation of individuals who knew each other and responded to each other, and were, in their own ancient way, present in the world. Let that image settle over you as you breathe. Small bright-eyed animals in ancient forests, their feathers catching the light in colours we are only now learning to read. The world alive with meaning, even then, even 125 million years ago. The feathers were not just for flying, they were for speaking, and the speaking was real. Sound in the ancient world would have been extraordinary. We tend to imagine prehistoric landscapes as silent, or filled only with the kind of ambient noise we associate with wilderness, wind through vegetation, the sound of water, the calls of insects, but the Cretaceous world in reality would have been filled with dinosaur sound. Rich, varied, layered sound of a complexity we are only beginning to understand. How do we know this? The evidence comes from multiple sources, and it converges on a picture that is both scientifically fascinating and, when you let yourself really imagine it, deeply evocative. Begin with anatomy. The skulls of many dinosaur species preserve structures that, when analysed, reveal unmistakable acoustic function. The most dramatic of these are the hollow crests of the hadrosaurs. Parasaurolophus walkeri, perhaps the most familiar of these species to popular audiences, carried a crest so large and so elaborately structured that researchers have been able to reconstruct, using computed tomography scans and computer modelling, exactly what sound it would have produced. The answer is a sound, unlike anything in the modern world. The crest of Parasaurolophus was essentially a long looping tube, a resonating chamber that would have amplified and shaped sound produced by the animal's vocal cords. The specific geometry of the tube determined the specific resonances. Computer models suggest that when Parasaurolophus vocalized through its crest, it produced a sound somewhere between a deep, rich foghorn and an organ pipe, a low, penetrating tone that could travel enormous distances and that would have carried distinctive individual and species-specific acoustic signatures. But here is what makes this particularly interesting. The crests of hadrosaurs varied enormously. Different species had different crest shapes, and within some species, there is evidence that males and females had differently shaped crests, and that the crests changed shape as animals grew. This variation would have produced variation in the sounds individual animals made. It would have made individuals acoustically distinct, recognizable by their voices, in a world where voice could carry information about identity, sex, age, and reproductive status. Parasaurolophus is the most dramatic example, but other hadrosaur genera show the same principle at work. Corythosaurus carried a crest like a rounded helmet, with internal chambers configured differently from those of Parasaurolophus, producing different acoustic signatures. Lambeosaurus had a hollow, forward-jutting crest that would have produced yet another range of sounds. The diversity of hadrosaur crests across dozens of species is, in acoustic terms, a diversity of voices. A radiation of communication systems built on the same basic anatomical platform, each species tuned to a different acoustic signature. This is not the behavior of animals with nothing to say. This is the behavior of animals for whom communication was so important, so central to social life, that evolution invested the anatomical equivalent of an entire musical instrument in each individual skull. And the hadrosaurs were not alone in this communicative elaboration. The ceratopsians, the horned dinosaurs, of which Triceratops is the most famous representative, also show elaborate display structures, the great bony frills and the prominent horns that gave the group its name. These structures have traditionally been interpreted primarily as defensive weapons, and there is no doubt they served defensive functions. But behavioral analysis of modern animals with similar structures suggests that display, communicative display, the transmission of information about identity, status, health, and reproductive condition, was at least equally important. The frills of ceratopsians show evidence in some species of rich blood vessel networks, structures that would have allowed the animals to flush their frills with blood, changing their colour or patterning rapidly. This is precisely what modern lizards and other reptiles do with their display structures. The dewlap of an anole lizard communicates identity, territory, and reproductive status through a rapid colour change that can be performed in a fraction of a second. If ceratopsian frills worked similarly, they were dynamic visual communication devices of considerable sophistication. The theropod dinosaurs, or the predators, communicated in ways that we can trace even more directly through their evolutionary descendants. Modern birds, again, are our best guide. The extraordinary diversity of bird vocalizations, the complexity of song, the specificity of alarm calls, the nuanced communication of individual recognition and social status, all of this evolved in the lineage that passed through the small theropod dinosaurs that survived the extinction and diversified into the 10,000 bird species we know today. The vocal apparatus of birds evolved from theropod anatomy. The syrinx, the bird's unique sound-producing structure, different in fundamental ways from the larynx of mammals, is present in all birds. Its evolutionary precursors were present in their dinosaur ancestors. The capacity for complex vocalization was being built in the theropod lineage long before the first bird appeared. What might have been communicated through these elaborate systems? The range of information conveyed through animal communication, even among animals we might not think of as sophisticated, is broader than most people appreciate. Prairie dogs, for instance, small rodents that seem to offer a sharp contrast to the magnificent complexity of dinosaurs, have been shown to communicate specific information about predators, not just the alarm call that says danger, but specific calls that convey information about predator size, shape, colour, and speed. Chimpanzees communicate emotional states, intentions, desires, and social relationships through a rich suite of vocalizations, facial expressions, and gestures. Elephants communicate across kilometers using infrasound, with calls that carry specific information about family groups, water sources, and the locations of other elephants. None of these animals use language the way humans do, but all of them communicate far more than we once assumed. The bar for what we credit animals with communicating has been rising steadily as research methodology has improved, and there is every reason to think that dinosaurs with their warm bodies and their complex social lives and their elaborate anatomical communication structures, communicated more than we give them credit for. There is one other element of dinosaur communication that deserves attention, and it connects the auditory and the visual in a particularly interesting way: colour. For a long time, we assumed dinosaurs were drab. The popular image, grey or green or brown, scaled and utilitarian, reflected both the limits of what fossilization can preserve and an implicit assumption that dinosaurs were not the kind of animals that needed to be colourful. But we were wrong. In the early 2000s, researchers developed techniques for analysing the microscopic structure of fossilized feathers, the melanosomes, the tiny cellular organelles that produce and contain pigment in feathers, can be preserved in fossilized feathers even over tens of millions of years. The shape of the melanosome determines the colour it produces, and those shapes are preserved in the fossil. This allowed, for the first time, an actual scientific determination of feather colour in extinct dinosaurs. The results were revelatory. Sinosauropteryx, a small feathered theropod from China, had alternating bands of reddish-brown and white on its tail, a pattern strikingly similar to those seen in display-oriented modern birds. Microraptor, a small four-winged theropod, appears to have had iridescent black feathers, similar to a modern starling. Anchiornis, another small-feathered dinosaur, sported a complex pattern of black and white with a reddish crest, a pattern that in a modern bird would scream display, information, and individual identity. These were not camouflage patterns, these were display patterns. These animals were advertising their species identity, their sex, their health, their reproductive status. They were communicating through colour in ways that required the ability to perceive colour, to interpret it, to respond to it. Modern birds, of course, have tetrachromatic vision, 4 types of colour receptors in their eyes, compared to 3 in most humans, allowing perception of ultraviolet light and a colour space far richer than anything we directly experience. The eyes of many theropod dinosaurs, preserved in exquisite detail in some fossils, show scleral ring structures similar to those of modern birds, suggesting comparable visual acuity and potentially comparable colour perception. A world seen through theropod eyes would have been visually rich beyond our imagining, a landscape of colours and patterns that carried information dense with social meaning, a visual language written not in words but in feather and light, and the precise geometry of display. When all of this is assembled, the acoustic communication of the hadrosaurs, the visual communication of the feathered theropods and the frilled ceratopsians, the social context in which all of this communication was embedded, what emerges is a picture of the Cretaceous world as a place alive with meaning, a place where animals were not merely reacting to immediate stimuli, but exchanging information, navigating social landscapes, building and maintaining relationships through the constant flow of signals transmitted and received. This is what language is, at its most fundamental level. Not words and grammar, those are the specific human implementation of a more general capacity. Language is the structured transmission of information between minds, and the evidence is now compelling that many dinosaurs were doing something that deserves, at minimum, to be placed on a continuum with language. Something that represents a genuine, rich, functional communication system. Not human language, not symbolic language, but communication of real complexity and expressiveness. A kind of mind meeting mind across the warm Cretaceous air. Let that image find you. Let it settle into your breathing. The ancient world was never silent. It was alive with the exchange of meaning, with the recognition of one another, with all the intricate music of social creatures living their complicated, connected lives. Rest into that sound, the low resonance of a hadrosaur calling across the floodplain, the soft rustle of feathers in the forest. The world, 66 million years gone, but no less real for that, humming with the continuous transaction of minds. We have been spending a great deal of time thinking about the small theropods, Troodon, the dromaeosaurids, the small feathered dinosaurs that were, in many ways, the most cognitively sophisticated of the non-avian dinosaurs. This makes evolutionary sense, since the small-bodied, large-brained theropods are the ones whose trajectories point most directly toward the kind of intelligence we find most recognizable. But the large dinosaurs deserve attention too. Not because they were the most cognitively sophisticated, the evidence does not clearly support that claim, but because our picture of their inner lives has been revised as dramatically as our picture of any other aspect of dinosaur biology, and the revision is, in its own way, just as astonishing. Begin with the giant sauropods: Brachiosaurus, Apatosaurus, Argentinosaurus, Patagotitan. These were the largest animals that ever walked the earth. Patagotitan majorum, the largest known species, may have weighed as much as 70 or 75 tons and stretched 30 meters from nose to tail. The scale of these animals is simply difficult to hold in the imagination. Their hearts were the size of small cars. Their footprints left craters in the earth. A single thigh bone, if set on end, would tower over most people. For a long time, our picture of these animals was of vast, dim creatures, physiologically impressive but cognitively rudimentary. Large bodies require efficient digestion of enormous quantities of plant matter. Much of the sauropod brain, it was assumed, was dedicated to simply managing the biological logistics of an animal that size. Anything recognizable as complex cognition seemed unlikely in an animal with a brain the size of a tennis ball, relative to a body of 70 tons. But this picture has required revision on several fronts. The first revision concerns the social lives of sauropods. Evidence from track sites around the world shows that sauropods moved in groups, not just loose aggregations, but organized groups with consistent spatial relationships between individuals. At multiple sites, trackways show juveniles walking close to adults, positioned in patterns that suggest the larger animals were providing some form of protection or guidance to the smaller ones. This is not random grouping. This is structured social behavior. The nesting evidence we have already discussed confirms this picture. Titanosaur nesting colonies, with their consistent nest spacing and evidence of repeated use of specific sites over many generations, imply social organization during reproduction. The timing of egg laying, the choice of nesting site, the spatial arrangement of nests, all of this points to social coordination that could not have been accidental. What level of cognitive sophistication is required for this kind of social organization in very large-bodied animals? The answer is not trivially small. Social living in groups, maintaining relationships, tracking the identities and relative statuses of multiple individuals, coordinating behavior with others, places genuine cognitive demands on any animal, regardless of its body size. The specific demands scale with the complexity of the social system, not with the size of the body. Elephants, the largest living land animals, have large and complex brains despite their large bodies. They are cognitively sophisticated in many dimensions. They show strong individual bonds, complex family social structures, remarkable spatial memory, emotional responses to death that include what appear to be grief behaviors. Elephants are not cognitively sophisticated because their brains are large in absolute terms, though they are. They are cognitively sophisticated because the social and ecological demands of their lives have driven the evolution of neural complexity. The social and ecological demands of sauropod life may have been more modest than those of elephants, but they were not zero, and the evidence increasingly suggests that the internal lives of even the largest sauropods were not as blank as we once assumed. There is evidence, from bone histology, of strong social bonds in at least some sauropod species. Studies of juvenile sauropod remains suggest they were not independent from birth. The pattern of their deaths, often in groups, suggests that young sauropods travelled and fed with other juvenile animals rather than being left entirely to fend for themselves. This pattern is consistent with extended social association, with the young learning the roots and resources of their landscape from more experienced animals. The long necks of sauropods, which reach their most extreme development in species like Brachiosaurus and Mamenchisaurus, have been the subject of considerable debate about their function. They are clearly adaptations for reaching food at heights unavailable to competitors, or for covering large areas of ground-level vegetation without moving the massive body. But some researchers have also suggested that long necks served display functions, that size and neck length communicated something important in the social world of sauropods: mate assessment, dominance signaling, individual recognition at distance across the open landscapes where large sauropod herds moved. If sauropod necks were partly display organs, then sauropods had a visual communication system, crude perhaps compared to the elaborate feather displays of theropods, but functional and socially meaningful, and a communication system, however simple, implies the cognitive machinery to produce and receive signals, to associate signals with individuals, to respond appropriately to different signal types. The emotional dimension of dinosaur life is perhaps the most speculative territory we can enter, but it is not entirely without evidence. Modern research on animal emotion has moved far from the conservative position of earlier decades, when attributing emotional states to animals was considered unscientific anthropomorphism. The neuroscience of emotion is now well enough understood that we can make confident statements about which brain structures support emotional processing and which animal lineages have those structures. The limbic system, the brain region most directly associated with emotional processing in mammals, has functional equivalents in birds and reptiles. Modern birds show clear behavioral and physiological evidence of emotional states, stress responses, positive affect during play and exploration, apparent grief behaviors following the loss of partners or companions. Crocodilians, which share a common ancestor with dinosaurs and are in many ways better proxies for dinosaur behavior than either mammals or birds, show surprisingly complex social bonds, play behaviors especially in young individuals, and what appears to be maternal attachment. If we use crocodilians and birds as brackets, the living lineages closest to dinosaurs, then the range of emotional capacity they suggest for non-avian dinosaurs includes the capacity for social bonding, especially between parents and offspring, the capacity for stress and fear responses, the capacity for something like pleasure in activities that are biologically rewarding, and possibly the capacity for individual-specific attachment, recognizing and preferring specific other animals over others. This is not a rich emotional life by human standards. It does not include the complex reflective emotions, guilt, shame, pride, existential anxiety, that depend on the specific neural architecture of the human prefrontal cortex and the specific cognitive capacities of human language and symbolic thought. But it is not nothing. It is a world of feeling, of social connection, of something that matters to the animal in a basic, embodied, real way. A young titanosaur that learned the migration route from its mother and followed her and stayed close to her in times of threat. That young animal was not indifferent to the relationship. Something in its neural architecture made that relationship valuable, rewarding, important. Something in its biology oriented it toward that specific individual, away from danger, towards safety. That is feeling. That is, in a very real sense, love. Not human love, not reflective and symbolic and articulate, but love in the deep ancient sense that existed before language, before abstraction, before everything that makes human emotion specific and particular. The warmth of proximity, the comfort of familiar presence, the pull toward the known and the trusted. This is what the large dinosaurs had, not the sophisticated cognitive life of Troodon, not the elaborate social intelligence of the hadrosaur herds, but something real, something warm, something that mattered. Rest with that for a moment. The giant animals of the ancient world were not empty of feeling. They moved through the world with their enormous bodies and their modest but real inner lives, and they knew in their own ancient way what they cared about. That is enough. That is everything, really. Let it be enough. There is one dinosaur that, above all others, has focused the minds of paleontologists and evolutionary biologists on the question of dinosaur intelligence. One species that, when you look at it carefully, makes the imagination do something vertiginous. That species is Troodon formosus. Troodon was a small theropod dinosaur from the late Cretaceous of North America, the same time and place as Tyrannosaurus rex, Triceratops, and the duckbill hadrosaurs. It was not large. Adults ranged from roughly 6 to 11 feet in length, and its weight was modest by dinosaur standards, perhaps 50 to 100 kilograms. It walked on 2 legs, had long, grasping hands with opposable-like grip capabilities, and it had, relative to its body size, a brain that was enormous. Not enormous in absolute terms. The brain of Troodon was small by human standards, but encephalization quotient, the standardized measure of brain size relative to body size that allows meaningful comparison across species of different dimensions, told a different story. Troodon had an EQ comparable to modern emus and ostriches. This might not sound impressive until you consider that emus and ostriches, like all modern retites, are among the less cognitively sophisticated of modern birds, and yet they are still considerably more capable than most non-avian animals. More tellingly, Some estimates of Troodon's EQ place it in the range of modern parrots and corvids, and modern parrots and corvids are, as we have noted, among the most cognitively sophisticated animals on the planet. Troodon also had large forward-facing eyes, significantly larger relative to skull size than most other dinosaurs. Forward-facing eyes mean overlapping visual fields. Overlapping visual fields mean binocular vision, and binocular vision means depth perception, the ability to accurately judge distance in 3 dimensions. This is a critical faculty for predators that need to accurately judge the position of fast-moving prey. But it is also a critical faculty for any animal engaging in precise, coordinated manipulation of objects in its environment. And Troodon's hands were remarkable. The digits were long, with the capability for a grip that, in some analyses, resembles nothing so much as a primitive version of the precision grip that in primates underlies tool use. The hands were not the tiny vestigial appendages of Tyrannosaurus rex. They were functional manipulators, hands that, in a warm-blooded, large-brained animal, might have been capable of things we have not yet fully imagined. The paleontologist Dale Russell, working in the late 1980s, asked what might seem like an irresponsible question. Given Troodon's trajectory, the direction in which its lineage appeared to be evolving in terms of brain size and body plan, where might that evolution have led, had the asteroid not intervened? Russell's thought experiment, published in 1988, produced what he called the Dinosauroid, a speculative reconstruction of what a Troodon-descended intelligent dinosaur might have looked like after another several million years of evolution. The Dinosauroid was bipedal, with a large domed skull housing a substantially enlarged brain, forward-facing eyes, grasping 3-fingered hands, and an overall body plan that had converged, through the independent logic of intelligence-related morphology, on something superficially humanoid. The Dinosauroid has been controversial. Some researchers think Russell overestimated the humanoid nature of such a hypothetical creature, and there are good arguments that an intelligent dinosaur would not necessarily have evolved toward human-like morphology. Intelligence can take many forms, and there is no reason to assume that the specific human body plan is the only scaffolding on which it can be built. But the underlying question that the Dinosauroid was meant to illustrate is one that the scientific community has not been able to dismiss. The question is this: given Troodon's brain-body ratio, its manipulative hands, its binocular vision, and the general trend in theropod evolution toward increased encephalization over the Cretaceous period, was something like genuine intelligence, genuine abstract cognition, genuinely emerging in the dinosaur lineage before it was cut short? The honest answer is, we do not know. The direct evidence is insufficient for certainty. We cannot open a Troodon skull and examine the folded complexity of its neural tissue. We cannot observe Troodon behavior. We have bones and impressions and inferences. But the inferences are suggestive in ways that go beyond Troodon alone. Consider the broader trend. If you map encephalization quotients across the theropod family tree, from the earliest theropods of the Triassic, through the various lineages of the Jurassic, and into the late Cretaceous, a pattern emerges. Brains were, in general, getting larger relative to body size over time. Not in every lineage, not in every branch, not uniformly. But the trend was there. Evolution was, in general, rewarding larger brains in theropods. This is exactly the pattern that preceded the evolution of high intelligence in mammals. Relative brain size in the mammalian lineage increased progressively over tens of millions of years, accelerating as social complexity increased and ecological pressures rewarded cognitive flexibility. The process culminated over 65 million years of post-Cretaceous mammalian evolution in the brains of primates and eventually humans. The theropod lineage was on a trajectory with some structural similarities to the mammalian one: larger brains, smaller bodies, increasingly sophisticated social behavior, increasingly complex communication. The asteroid interrupted that trajectory at a particular point. Where it would have led is genuinely unknown, but here is a number that should give you pause. The asteroid hit 66 million years ago. The theropod lineage had been evolving toward increased intelligence for roughly 90 million years by that point. Modern human intelligence, the specific kind of recursive, symbolic, language-based cognition that defines us, evolved in a lineage that had been building toward it for roughly 65 million years since that same asteroid wiped out the large non-avian dinosaurs. We emerged in 65 million years. The theropods had 90 million years behind them, and they were not starting from zero. This is not a claim that Troodon was intelligent in the way humans are intelligent. It emphatically is not. The gulf between what Troodon actually was and what humans actually are is almost certainly vast, but it is a claim that the theropod lineage had already covered considerable evolutionary ground in the direction of intelligence, that the raw material was there, that the process was underway, and that the universe, had it moved, its rocks slightly differently, might have produced something we cannot quite imagine. The thought is one to sit with, not anxiously, not with any urgency, just as a quiet astonishment, the way you might hold a stone that turns out to be unexpectedly beautiful when you turn it in the light. Something almost happened, something almost emerged here on this planet that would have been different from us, but that would also have been, in some sense, one of us. A mind in the world, aware of the world, asking questions about the world. The asteroid wrote one story. There are other stories that might have been written. Rest with that quiet thought. The night around you is full of small sounds, small movements, the continuing life of the world. And somewhere in the deep past, moving through a world of extraordinary beauty and danger and complexity, a small feathered animal with large eyes and clever hands was navigating its world with a kind of awareness we are still learning to recognize. Sleep, when it comes, may carry strange and beautiful dreams. To fully appreciate what the advanced behavior of dinosaurs meant, we need to understand the world they were building it in. The Cretaceous period, from 145 million years ago to 66 million years ago, was not a static, simple backdrop for the dinosaur drama. It was one of the most dynamically evolving ecosystems in Earth's history, a world of extraordinary ecological complexity, ongoing biological innovation, and rapidly changing relationships between organisms. And dinosaurs were not passive inhabitants of that world. They were among its architects. The Cretaceous is the period during which flowering plants, the angiosperms, first appeared and then spread to dominate terrestrial vegetation worldwide. This is one of the most significant events in the history of land life, and its causes and consequences were deeply intertwined with the dinosaurs. Flowering plants evolved specific relationships with animals. Flowers attract pollinators, initially insects, eventually birds and mammals, by offering nectar and pollen as food rewards. Fruits attract seed dispersers by wrapping seeds in nutritious, appealing packages that animals will carry away and eat, depositing the seeds at a distance from the parent plant. These mutualistic relationships drove the coevolution of plants and animals in ways that transformed entire ecosystems. The herbivorous dinosaurs were, among all the Cretaceous animals, the most significant modifiers of vegetation. Large hadrosaur herds, moving through forested and open landscapes, consumed enormous quantities of plant matter, trampled vegetation, disturbed soils, and left concentrated deposits of nutrients in their dung. This disturbance ecology, the modification of habitat by the movement and feeding of large animals, is something we see clearly in modern ecosystems. African elephants maintain savanna ecosystems by breaking trees and preventing forest encroachment. Wildebeest herds on the Serengeti fertilize grasslands with their dung and maintain grass diversity through grazing pressure. Cretaceous dinosaurs would have had comparable effects. Their movements and feeding patterns shaped the vegetation, and the shaped vegetation in turn shaped the opportunities for other species. A hadrosaur herd passing through a forest edge, feeding heavily on low-growing vegetation and disturbing the soil, created open patches where fast-growing, light-loving plants could establish, including, potentially, the early angiosperms that were beginning their spread. This kind of ecosystem engineering by large herbivores is not just a matter of physical disturbance. It creates opportunities and constraints for other species, drives the evolution of plant defenses and animal feeding adaptations, and generates the ecological complexity that supports high overall biodiversity. The Cretaceous world, shaped in part by the behavior of its enormous dinosaur inhabitants, was extraordinarily diverse, and that diversity created the ecological context for sophisticated behavior. Complex ecosystems place complex demands on the animals within them. An animal living in a world with many food sources, many predators, many potential competitors, many social partners, and many environmental variables to track and respond to is under persistent selection pressure to develop the cognitive tools to manage that complexity. The Cretaceous world was getting more complex over time, not less. The diversification of flowering plants was driving the diversification of insects. New insect groups were appearing and spreading. New feeding strategies were being invented. The web of ecological relationships was thickening, becoming more intricate, generating more and more specific niches that required more and more specific adaptations. Into this increasingly complex world, the increasingly sophisticated cognitive capacities of the late Cretaceous dinosaurs were not a luxury. They were a response to ecological demand. The complexity of the world was teaching the animals within it to be more complex themselves. Consider what a hadrosaur moving through a late Cretaceous landscape needed to know. It needed to know the locations of food plants, not just generically, but specifically, where in this landscape the most nutritious plants were, where the most abundant patches were, which patches would be available in which seasons. It needed to know the movements and habits of predators, the territories of the tyrannosaurs, the hunting patterns of the dromaeosaurids, the specific signs of danger in the local environment. It needed to know its social world, the individuals in its herd, their identities and relative statuses, the complex of relationships and alliances that structured daily life. And it needed to know the physical landscape at a level of detail that would allow it to navigate, escape, and find resources across a range of many dozens or hundreds of square kilometers. This is an enormous cognitive load. Managing it requires memory, a great deal of memory, organized and accessible and continuously updated. It requires pattern recognition, the ability to extract regularities from experience and use them to predict future states. It requires social intelligence, the ability to model the behavior of others, anticipate their responses, and adjust one's own behavior accordingly. These are not simple tasks. They are the tasks that, in the mammalian lineage, drove the evolution of increasingly large and complex brains over tens of millions of years. They were also apparently the tasks that the late Cretaceous dinosaurs were facing in a world of increasing ecological complexity. The arms race between predator and prey is one of the most powerful engines of cognitive evolution. Predators that can predict the behavior of their prey catch more of them. Prey that can predict the behavior of predators survive more often. Each cognitive advance by one side places pressure on the other side to match or exceed it. In a world with sophisticated predators and sophisticated prey, the cognitive bar is continuously being raised. The late Cretaceous had some of the most sophisticated predators in Earth's history. Tyrannosaurs were not simple sit-and-wait ambushers. Their anatomy, powerful hind limbs, sensory equipment suggesting excellent olfaction and vision, the forward-facing eyes of a binocular predator, is consistent with active hunting strategies that required tracking prey, learning their movements, possibly coordinating with others of their kind. And the prey, the hadrosaurs, the ceratopsians, the smaller ornithopods, were under correspondingly strong selection pressure for the cognitive tools to survive these predators. Better memory of predator territories, better alarm signal systems, better coordinated responses to threat, better judgment of when to flee and when to stand and defend. This cognitive arms race was playing out in a world that was, moment by moment and season by season, presenting new challenges, new variations, new demands for flexibility and learning. The late Cretaceous ecosystem was a crucible for cognitive evolution, and the animals moving through it were being shaped by it in real time. What emerged, by the final millions of years of the Cretaceous, was an ecosystem of extraordinary biological sophistication. Plants and animals co-evolved across millions of years of interaction, each group bearing the marks of the other's influence. And within that ecosystem, the dinosaurs were not just the largest and most spectacular animals. They were the most cognitively complex, the most behaviorally elaborate, the most socially sophisticated vertebrates that terrestrial ecosystems had yet produced. That is worth sitting with. The word sophisticated does not quite do justice to what the late Cretaceous terrestrial ecosystem was. It was something never seen before on land, a richly co-evolved community of large-brained, warm-blooded, socially complex, behaviorally flexible animals navigating an extraordinarily diverse ecological world. It was, in retrospect, a rehearsal, a grand, extended 66-million-year rehearsal for what would come after, the mammalian world, the world that eventually produced us. But it was also its own thing, complete in itself. The dinosaurs were not practicing for the future. They were living their own present. their own long, complex, beautiful present that lasted for 165 million years, and that was, for all its strangeness and distance from us, genuinely alive in every sense of the word. Breathe that in slowly, the complexity of the ancient world, the aliveness of it, teeming and elaborate and real. The night continues around you. Somewhere outside, a bird is doing what birds do at night, sleeping in a tree, small and warm and ancient, dreaming its bird dreams. And the ancestors of that bird, in a world you cannot visit but can imagine, were doing the same thing in the warm Cretaceous dark. Sleep is old. Life is old. The world is very old, and full of a continuity that we are only beginning to appreciate. Rest into it. Rest into the long, slow, patient continuity of life. There is a river in Argentina. Its name is the Neuquén, and it flows through some of the most productive dinosaur fossil country on the planet, the arid badlands of Patagonia, where the rock is the right age and the erosion is persistent, and the secrets buried in the earth are constantly being exposed by wind and time. Along the banks of the Neuquén and its tributaries, paleontologists have found titanosaur nesting sites, the preserved evidence of massive sauropod dinosaurs gathering together to lay their eggs in organized structured nesting colonies. These were enormous animals. Titanosaurs were among the largest, creatures ever to walk the earth, some species stretching to lengths of 30 meters and weights of 50 or 60 tons. The logistics of their reproduction alone would have been staggering, and yet, what the fossil evidence suggests is that they did not simply wander into any convenient patch of ground and deposit their eggs at random. They gathered at specific sites. Year after year, generation after generation, the same sites were used. The evidence of deep stratification, layer upon layer of nest horizons in the same locations, shows that these places were used repeatedly over very long periods. How does an animal return to a nesting site? How does it know where to go? Memory. Specifically, the kind of spatial memory that in modern animals is associated with the hippocampus and related brain structures. The ability to encode, retain, and recall information about specific places in the landscape over long periods of time. We know that modern birds have remarkable spatial memory. Clark's nutcrackers, small corvid relatives that cache food in hundreds or thousands of locations over a wide area, can remember the locations of individual caches for months, retrieving them through winter with remarkable accuracy. Homing pigeons navigate back to their lofts from hundreds of kilometers away using a combination of magnetic field detection, visual landmarks, and infrasound mapping. Sea turtles return across entire ocean basins to the beaches where they were born to lay their own eggs, guided by magnetic memories laid down in their earliest days of life. If titanosaurs returned to specific nesting sites across years or decades of adult life, they were doing something similar, maintaining a spatial memory of sufficient fidelity to navigate to a specific location that might be hundreds of kilometers from their daily ranges. This is not a trivial cognitive feat. It is evidence of a kind of episodic-like memory, the retention of specific, localized information over long time spans. An episodic memory is one of the cognitive capacities that has been most closely linked to higher-order cognition. It is the capacity that underlies planning, the ability to project forward in time by drawing on memories of the past. It is the capacity that underlies learning from experience, the ability to update behavior based on remembered outcomes. It is, in short, one of the building blocks of intelligence. The spatial memory implied by titanosaur nesting site fidelity is one line of evidence. But there are others, and together they build a picture of dinosaur memory and learning that is considerably richer than the blank reactive cognition we once attributed to these animals. Consider the developmental evidence. Animals with extended periods of parental care, and we have seen that many dinosaurs provided substantial parental care, undergo qualitatively different cognitive development from animals that are independent from birth. The period of dependence is a period of intensive social learning, in which juveniles are continuously acquiring behavioral information from experienced adults. This is not just information about what to eat and what to fear, though those are certainly part of it. It is information about social relationships, who to trust, who to defer to, what the signals of dominance and submission mean, how to navigate the complex social landscape of the group. Social learning of this kind requires, first, the ability to observe and encode the behavior of others. It requires the ability to extract the relevant pattern from the behavior, not just to see what another animal does, but but to understand at some level why, and it requires the ability to store that extracted pattern and apply it in novel situations. These are non-trivial cognitive operations. Modern birds and mammals that engage in extended social learning demonstrate these capacities clearly. Young chimpanzees spend years observing and practicing tool use, gradually acquiring skills that cannot be reinvented independently by each generation. Young crows observe and modify their behavior based on what they see other crows do, including, in a remarkable demonstration of social transmission, the use and modification of tools. Young whales learn migration routes, feeding techniques, and even dialects of song from their mothers and other experienced group members. If young Maiasaura spent extended periods in the nesting colony under the guidance of experienced adults, learning the landscape, the social structure, and the behavioral norms of their group, they were engaged in something functionally similar. Not identical to chimpanzee or crow social learning, certainly, but operating on the same basic cognitive platform: observe, encode, recall, apply. The ecological scale of dinosaur ranges gives this learning special significance. We know from trackway evidence, from the distribution of fossils and from comparison with modern large animals that many dinosaurs undertook substantial migrations. Seasonal movements following food resources, water sources, and nesting opportunities across landscapes of enormous extent. A hadrosaur herd moving from summer feeding grounds to winter lowland refuges might have traversed hundreds of kilometers in each direction. This route was not instinctive, not hardwired in the way salmon are hardwired to follow chemical gradients upstream. It was learned, it was transmitted. An experienced adult in the herd carried in its memory not just the current destination, but the entire path. The specific river crossings, the particular valley routes, the water sources that appeared and disappeared with the seasons, the danger spots and the safe corridors. This knowledge was the herd's most valuable resource, and it was housed in the memory of specific individuals. This has profound implications for what the loss of experienced adults would have meant to a herd. In African elephant herds, it has been demonstrated that groups with older, experienced matriarchs navigate more successfully, respond more appropriately to threats, and show better survival outcomes during crises like droughts. The matriarch's memory is the group's collective intelligence, her experience a resource that benefits every individual in the herd. There is no reason to think dinosaur herds were categorically different. The experienced adults who had travelled the migration route many times, who knew where the predators denned and where the river crossings were safe, who recognized the signs of seasonal change and could read the landscape signals, these individuals were cognitively valuable members of the group in ways that their physical attributes alone do not capture. And then there is the question of cultural transmission, the passage of learned behaviours from generation to generation in ways that allow cumulative change over time. This is, in humans, the foundation of culture and technology. But it is not unique to humans. We know that chimpanzees have culturally distinct tool use traditions that vary from group to group and are transmitted through social learning across generations. We know that songbirds have culturally transmitted song dialects that evolve over time as individuals learn from and modify the songs they hear. We know that cetaceans, dolphins and whales, have culturally transmitted feeding techniques, social behaviours, and vocal traditions. Did dinosaurs have something like culture? The evidence is, by its nature, indirect and limited. Culture leaves few direct traces in the fossil record, but the structural preconditions, social learning, parental care, long lives with extended periods of skill and knowledge acquisition, appear to have been present in many dinosaur species. Consider what it would mean if the knowledge that a titanosaur herd carried about their migration routes was genuinely culturally transmitted, passed from experienced adults to younger animals, modified slightly by each generation's experience, accumulated over decades and centuries. The nesting sites that were used generation after generation along the New Cairn were not just remembered by individual animals, they were known, in a deep sense, known in the way a human community knows the paths its ancestors walked, the places where it is safe and the places where it is not. Not in words, not consciously, in the way we're conscious of our own knowledge, but known in the way that deep experience makes itself felt, in the sureness of movement, the confidence of direction, the recognition of familiar landmarks by animals who have not, themselves, been here before, but whose mothers and grandmothers and great-grandmothers walked this path before them. This is what knowledge is, at its most ancient and essential. This is what memory is for. Let that thought move through you slowly. Let it become part of the rhythm of your breathing. Somewhere in the deep past, in the warm Cretaceous afternoon, a young dinosaur was learning the world from the animals who had lived in it longest, was laying down the memories that would guide a long life, was receiving, through 100 small moments of observation and imitation and gradual mastery, the accumulated wisdom of generations. The ancient world was not empty of knowledge. It was full of it, full of everything that had been learned and remembered and passed on. Sleep gently into that thought. The world has been remembering itself for a very long time. There is a behavior that, perhaps more than any other, signals the presence of the kind of cognitive complexity we associate with sophisticated mental life. It is a behavior that is, in some ways, profoundly inefficient, wasteful of energy, apparently purposeless, often risky. And yet it appears reliably in every lineage we recognize as cognitively sophisticated. That behavior is play. Play is not a trivial topic in behavioral biology. It is one of the most studied and most theorized phenomena in animal behavior, precisely because it seems, on the surface, to make no sense. Natural selection is supposed to favor efficiency, to select for behaviors that maximize survival and reproduction relative to cost. Play is costly. It uses energy, exposes the player to predation risk, sometimes results in injury. And yet play appears in mammals, in birds, in some fish, in some cephalopods. It appears in highly cognitively sophisticated animals across phylogenetically diverse lineages. The consensus answer to the question of why play exists is that it is not actually wasteful at all. It is the neural machinery of learning and development running at maximum capacity, generating and testing behavioral repertoires in conditions of relative safety, building the skills and mental models that will be essential for survival in adulthood. Play is how complex brains learn, through exploration, through variation, through the testing of possibilities in a context where the consequences are not final. Young mammals play extensively, and the specific patterns of their play reflect the specific demands of their adult behavioral repertoire. Young predatory mammals play fight, practicing the motor skills and tactical thinking they will need as hunters. Young prey mammals play in ways that develop evasion skills and social coordination. Young primates engage in complex social play that develops the theory of mind abilities, relationship skills, and cognitive flexibility they will need to navigate complex social groups. Young birds play too, though their play is somewhat different in character, reflecting the different developmental and behavioral demands of avian life. Juvenile crows and ravens play elaborate games, dropping and catching objects in the air, rolling on their backs, engaging in apparent social play with siblings and peers. Young parrots play with objects, experimenting, with manipulation in ways that develop their tool cognition and fine motor skills. These play behaviors are not incidental to bird cognitive development. They are essential to it. Did dinosaurs play? The direct fossil evidence for play behavior is essentially non-existent. Play leaves very few traces in the fossil record. No distinctive bone shapes, no unique taphonomic signatures, nothing that preserves in stone the memory of a juvenile troodon chasing another juvenile troodon in the Cretaceous afternoon. But we can approach the question through the indirect evidence of developmental biology and behavioral ecology. The first line of evidence concerns the extended juvenile period. Play is most prominent in animals with extended juvenile periods, long developmental phases during which the young animal is not yet fully independent. The length of the juvenile period is closely correlated with the degree of behavioral complexity in adults. More complex adult behavior requires a longer developmental period to acquire. The evidence from bone histology, the growth rings preserved in dinosaur bone that allow paleontologists to estimate the age of individuals at death, suggests that many dinosaurs had extended juvenile periods by reptile standards. Large theropods and sauropods grew relatively slowly after an initial fast growth phase, reaching full size over many years. This extended growth period, during which the animals were smaller than adults, and therefore under different predation pressures and in different social positions, provided the temporal space in which play-based learning could occur. The second line of evidence is the presence of parental care. Play in young animals is facilitated by parental tolerance and protection. Parents who guard the young create safe contexts in which exploration and experimentation are possible without immediate fatal consequences. The evidence for parental care in multiple dinosaur lineages, which we have reviewed in earlier acts of this story, implies the existence of protected developmental contexts in which play-like behaviour could occur. The third line of evidence is the comparison with modern relatives. Both crocodilians and birds show juvenile play behaviour. Juvenile crocodilians, though they are not among the most cognitively sophisticated of modern animals, play in ways that include social play and object manipulation. Juvenile corvids, parrots, and other cognitively sophisticated birds engage in elaborate play that is strikingly similar in its structure to the play of young mammals. Given that both the closest living relatives of non-avian dinosaurs show juvenile play, and given the evolutionary distance between these two groups, the inference that play was present in some form in the dinosaurs between them seems reasonable. What might dinosaur play have looked like? In young theropods, play likely included forms of motor practice, the running, jumping and tumbling that young active animals do when they are not under immediate threat. Social play between siblings or age mates in a nesting colony would have been the context for early development of the social cognition that adult life would demand. Young hadrosaurs in a nesting colony, the evidence of which is so clear at Egg Mountain, would have been in close proximity to siblings and other juveniles for extended periods, exactly the social context in which play behaviour occurs. For the small, bright-eyed, grasping-handed theropods, play may have included object manipulation, picking up and examining and dropping small objects in the kind of exploratory behaviour that in young mammals and young corvids is a precursor to tool use and complex problem-solving. We cannot document this from fossils, but the anatomy, those grasping hands, those large eyes, those enlarged brains, is the anatomy of animals that, when they were young and safe and fed, would have had both the capacity and the time for exactly this kind of exploration. There is something in the image of a young Troodon in the Cretaceous afternoon, playing with a pebble or a fallen stick in the dappled light of an ancient forest, that is recognisable across the enormous gulf of time. Not human, not equivalent to the play of a human child, but not wholly alien either. Something that would not look entirely different, in its basic character, from any other young warm-blooded animal making the most of a quiet afternoon. Play is how brains grow into what they need to be. And in the dinosaur lineages that were building toward cognitive complexity, play was presumably doing exactly that work, filling the neural architecture being laid down by warm blood and active metabolism and extended development with the patterns and procedures and flexibilities that would be needed in the complex adult world. The ancient world had play in it. The Cretaceous afternoon had in it the sound of young animals at play, the quick movements of exploration and practice, the social energy of siblings testing each other and testing the world. This is not just a poetic thought. It is, given everything we know about development and cognition and the evolutionary biology of play, the most parsimonious reading of the evidence. Play is old. Joy, or something deeply ancestral to what we call joy, is old. Let that thought settle over you as your breathing slows and your body relaxes. The world is full of old joys, of ancient expressions of the same underlying thing, the pleasure that complex brains take in their own activity, in the exploration and mastery of possibility. You are doing it now, in a way, the mind following a story, following wonder, following the pleasure of knowing and imagining. This is also a kind of play. This is also the brain doing what it does best, ranging freely through possibility, building new patterns from new material. And 120 million years ago, in a world you cannot visit, other minds were doing something of the same kind. Rest into the ancient playfulness of the world. Let it carry you like a warm current into sleep. Close your eyes and try to imagine the world as something other than what you know it to be. We move through a world shaped primarily by vision, a world of colour and form and the play of light over surfaces. When we try to imagine how other animals perceive the world, we tend to imagine a dimmer or brighter, or differently coloured version of what we see. But the reality of sensory experience across the animal kingdom is far stranger and more various than that. The world of a bat is built primarily of sound, of echoes returning from surfaces in the dark. The world of a star-nosed mole is a world of texture and vibration, its extraordinary nasal star a sensory organ of unparalleled sensitivity to the physical substance of the soil. The world of a shark is electrified, lit by the faint bioelectric fields of living organisms. The sensory world of dinosaurs was different from ours, and understanding how they perceive their world tells us something important about how they navigated it, and therefore about the cognitive demands that their environment placed on them. Begin with vision. We have already touched on the evidence for colour vision in theropod dinosaurs and the elaborate display coloration preserved in feathered fossils, but the story of dinosaur vision goes deeper than colour. The structure of dinosaur eyes, preserved in exceptional detail in some fossil specimens, tells us that many species had large eyes relative to their skull size. Large eyes are, in general, an adaptation to conditions where maximising light capture is important, dim light, or the need to detect small or fast-moving objects at distance. Many predatory theropods had very large eyes, consistent with the hypothesis that they were active in conditions of reduced light, dawn and dusk, or even night. The sclerotic rings, bony rings embedded in the iris, preserved in many dinosaur specimens, tell us even more. The diameter and shape of the sclerotic ring determine the aperture and focal length of the eye, and these parameters together define the visual performance of the system. Analysis of sclerotic rings in different dinosaur species has revealed a striking diversity of visual systems, with different species apparently adapted to activity at different times of day. Tyrannosaurus rex, in some analyses, appears to have had visual capabilities consistent with activity across a wide range of light conditions, including something approaching the visual performance of modern raptors, which are famously acute-visioned predators. Troodon, with its enormous eyes, appears to have been adapted for very low-light conditions. A nocturnal or crepuscular hunter, operating in the dark or twilight with vision that may have been exceptional by any standard, forward-facing eyes positioned to give. Overlapping visual fields and therefore stereoscopic depth perception appear in multiple lineages of small theropods. Troodon had them. Several of the small bird-like dromaeosaurids appear to have had them, and the cognitive significance of binocular vision is considerable. Stereopsis, the perception of depth from the slightly different views provided by two forward-facing eyes, is a computationally demanding perceptual task. It requires the brain to take two slightly different images and extract from their differences precise information about the three-dimensional structure of the world. It requires, in short, a brain that is doing something quite sophisticated with the sensory information it receives. Animals with well-developed binocular vision tend to be either predators that need precise three-dimensional information about prey, or animals that engage in complex manipulation of objects. In primates, the evolution of stereopsis is closely linked to the evolution of precise hand-eye coordination, the ability to reach accurately for objects in space, to manipulate small items with precision. In owls and hawks, it supports the precise timing of a strike. For a small theropod with grasping hands and binocular vision, both functions may have been relevant. Precise striking of fast-moving prey, and perhaps also, intriguingly, the manipulation of objects in ways that might, in the fullness of evolutionary time, have become something more. Smell was also important. The olfactory bulbs of many dinosaurs, the brain regions dedicated to processing olfactory information, were substantial, particularly in the larger predators. Tyrannosaurs in particular show large olfactory bulbs in their endocasts, suggesting that smell was a primary sensory modality for tracking prey and navigating their environment. Modern crocodilians, which share a common ancestor with dinosaurs, have extraordinary olfactory sensitivity, and it seems likely that many dinosaurs were similarly gifted in this dimension. But perhaps the most fascinating element of dinosaur sensory biology is one that is not about the conventional senses at all. It is about hearing, and specifically about infrasound. Infrasound, sound at frequencies below the threshold of human hearing, typically below 20 Hz, travels extraordinary distances through both air and ground. Elephants are the best-known users of infrasound among modern mammals. They communicate across distances of kilometers using calls with infrasonic components, their large bodies and specialized hearing systems tuned to these long-distance acoustic channels. But infrasound communication is also documented in several bird species, in alligators and crocodilians, and in a number of other animals. The hadrosaurs, with their hollow crests, appear to have been capable of producing sounds across a wide range of frequencies, including potentially infrasonic components. The resonance properties of the crests, as reconstructed by computer modeling, suggest that at maximum volume, hadrosaur vocalizations would have included infrasonic components that could have carried over distances of many kilometers. Consider what this means for a herd of hadrosaurs moving across the Cretaceous landscape. Individual animals could potentially maintain acoustic contact with each other, and with other hadrosaurs far outside visual range, through infrasonic calls that humans could not hear. A predator detected at the edge of the herd's territory could trigger an infrasonic alarm response that would reach animals kilometers away before the predator itself did. Migration routes could be communicated acoustically across vast distances. Individual identity and reproductive status could be broadcast over ranges that the animal's eyes could never cover. The hadrosaur world would have been, in this sense, acoustically much larger than it appeared visually. The meaningful perceptual space of a hadrosaur herd extended not just to the horizon, but potentially for kilometers in every direction, populated by the voices of animals too distant to see, but close enough, acoustically, to be part of the social world. This is not a simple sensory system. This is an extended sensory ecology of considerable sophistication. And it requires, to be used effectively, a brain that can track multiple simultaneous acoustic sources, extract identity information from vocal signatures, integrate that information with spatial memory of the landscape, and generate appropriate behavioral responses to acoustic signals of different kinds. This is what brains do when they are built for this. When evolution has spent sufficient time selecting for these capacities, and in the hadrosaurs, as in many other dinosaur lineages, the evidence suggests that this is exactly what happened. There is something else worth noting about sensory experience and cognition. The richness of sensory input is itself a driver of cognitive complexity. An animal living in a sensory world of great richness and variety, a world with many different kinds of information arriving through many channels, all requiring integration and interpretation, is under persistent selection pressure to develop the neural machinery to handle that information. The complexity of the world is, in this sense, a teacher. It writes complexity into the brain. The world that dinosaurs inhabited was, by any measure, sensory rich. The Cretaceous was a period of extraordinary ecological diversity. Flowering plants were just beginning their explosive radiation, adding new visual and olfactory complexity to the landscape. Insect diversity was enormous and growing, and the animals themselves, with their elaborate crests and frills and feathers and vocalizations, were continuously enriching each other's sensory worlds. In such a world, the selection pressure for sensory sophistication and for the cognitive machinery to use it would have been intense and continuous. The brains of many dinosaurs, we are increasingly convinced, were doing much more than we once assumed. Let that richness find you now, as you rest. The sensory world around you is extraordinary. The small sounds of the night, the ambient temperature of the air, the weight of your body against what holds you. These are your senses reporting the world to you as you drift towards sleep. And somewhere in the deep past other senses were reading other worlds, worlds of infrasonic thunder and feathered colour, of chemical complexity and the precise geometry of starlight. Worlds we cannot enter, but which were real and rich and full for the animals who moved through them. Rest now into the richness. Let it carry you gently forward into sleep. 66 million years ago, on a Tuesday in geological terms, a rock approximately 10 kilometers wide arrived from the asteroid belt at a velocity of roughly 20 kilometers per second and struck the shallow, carbonate platform of what is now the Yucatan Peninsula in Mexico. The energy released by the impact was equivalent to roughly 1 billion atomic bombs. The explosion vaporized the impactor itself, excavated a crater 150 kilometers wide, and sent billions of tons of material into the atmosphere at speeds sufficient to reach orbital altitude. Some of that material fell back into the atmosphere on trajectories that converted kinetic energy to heat as it re-entered, heating the upper atmosphere sufficiently that, for hours after the impact, the sky rained fire across a significant fraction of the planet. The wildfires that resulted consumed forests across entire continents. Then came the darkness. The combination of dust, soot, and aerosols in the upper atmosphere blocked sunlight so effectively that global temperatures dropped precipitously, by some estimates, as much as 15 to 20 degrees Celsius globally, sustained over months and years. Photosynthesis became impossible over much of the planet. The food chains that depended on photosynthesis collapsed from the bottom up, and the animals at the tops of those food chains, the large, warm-blooded, metabolically expensive animals that needed the most food, died first and in the greatest numbers. Within a few 100,000 years, an eye blink in geological terms, roughly 3/4 of all species on Earth were extinct. Every non-avian dinosaur was gone. Along with the non-avian dinosaurs went the pterosaurs, most of the large marine reptiles, a great many fish species, most of the large mammals, a significant fraction of insects and plants. The world that emerged from the extinction was impoverished. Stripped of most of its large organisms, its food webs reduced to the most basic and resilient components. But it was not dead, and in its emptiness, evolution found opportunity. The small mammals that survived the impact, nocturnal, burrowing, able to subsist on insects and seeds and roots in a world without sunlight, were positioned, as it turned out, perfectly for what came next. When the darkness eventually lifted and photosynthesis resumed, and food webs began to rebuild, these small mammals found themselves in a world with almost no large animal competitors. Every ecological niche that had been occupied by a dinosaur was now empty. Every evolutionary opportunity that had been closed off by the dominance of the dinosaurian body plan was suddenly open. In 65 million years, the mammals have occupied every one of those niches and built new ones besides. They have evolved into whales, elephants, bats, and human beings. They have produced in multiple lineages independently the kind of cognitive sophistication that we have been attributing to the most advanced of the non-avian dinosaurs. And then they have gone considerably further, producing in the primate lineage, and eventually in ours, something that the dinosaurs never reached: symbolic language and the specific kind of abstract, recursive, culturally transmitted intelligence that comes with it. This is not a story of inevitable progress. The mammals did not advance beyond the dinosaurs because mammals are inherently superior. They succeeded because they survived, and because they happened to have life history traits: small body size, physiological flexibility, omnivory, that allowed survival in the aftermath of the asteroid. Had the asteroid not arrived, had the dinosaurs continued on their evolutionary trajectories for another 65 million years, the question of whether they might have reached what the mammals eventually reached is genuine. We have explored that question at length. The answer remains genuinely unknown. But the extinction is not simply a story of ending. It is also a story of beginning. And it tells us something important about the nature of intelligence and its place in the living world. Intelligence evolved in the mammalian lineage because the post-Cretaceous world rewarded it. The ecological and social pressures of the Cenozoic, the diversifying plant communities, the increasing complexity of predator-prey relationships, the intensifying competition among increasingly large-brained mammalian social groups, all drove the evolution of greater and greater cognitive sophistication. The specific path was contingent, unpredictable, shaped by countless accidents of ecology and climate and chance evolutionary events. But the general tendency, the tendency for evolution, given sufficient complexity of ecological and social context, to push toward greater cognitive sophistication, is not accidental. It is a reliable feature of the evolutionary process, appearing independently in multiple lineages, on multiple continents, in multiple ecological contexts. The dinosaurs showed it. The mammals showed it again. The birds, who are, we must remember, dinosaurs, showed it a third time in the corvids and parrots and other cognitively sophisticated avians. Dolphins and orcas showed it in the ocean. Elephants showed it on land. Intelligence is not the goal of evolution. Evolution has no goals. But intelligence is something that evolution finds repeatedly when it's operating in environments of sufficient complexity with organisms of sufficient biological sophistication. It is a kind of attractor in the space of possible evolutionary outcomes, something that many different trajectories converge on, not because it is inevitable, but because the conditions that favour it are widespread and recurrent. The asteroid ended one expression of this tendency, but the tendency itself did not end. It continued in the birds, which are dinosaurs. It continued in the mammals. It continues today in the cognitive sophistication of living corvids and cetaceans and primates, and it continues in you. The specific kind of abstract, linguistically mediated, culturally embedded intelligence that you possess is the current leading edge of a process that has been underway for a very long time. You are, in this sense, the most recent expression of something ancient, of the universe's tendency, given the right conditions, to produce minds. This is both humbling and significant. You are not the first mind in the history of this planet. You are not even the first sophisticated mind. You are one expression among many of a tendency that has been manifesting for 165 million years that we can document, and much longer in the broader sweep of animal evolution. But you are the expression that has gone furthest, and you are the expression that is capable of knowing its own history, of asking questions about itself and the world, of tracing the ancient roots of its own existence back through time to the small feathered theropods and the warm Cretaceous forests. That capacity, the capacity to know and to ask, is something genuinely new. It did not exist in Troodon. It did not exist in the intelligent mammals of the Eocene or the Oligocene. It emerged in the primate lineage over the last few million years, and it is extraordinary. It is the thing that allows you to be here, tonight, listening to a story about the deep past. It is the thing that connects you, through the long chain of knowing, to everything that came before. Hold that thought gently as you move towards sleep. You are the universe knowing itself, in one small, specific, temporary and remarkable instance. You are the current endpoint, the most recent node in a network of awareness that extends back through geological time. That is not a burden. That is a gift. Sleep well with it. Let the knowing rest, and let the dreaming begin. There is a question that paleontologists sometimes call the most tantalizing in all of science. It goes like this. Had the asteroid that struck the Yucatan Peninsula 66 million years ago arrived just a few minutes earlier, or a few minutes later, had it struck the deep ocean rather than the shallow continental shelf, releasing less sulfur and therefore less climate-altering aerosol into the atmosphere? Had the impact been slightly different in any of a dozen ways that might have made it slightly less globally catastrophic, what would have happened next? What would have happened to the dinosaurs if they had been given more time? This is not a frivolous question. It is a question about the trajectories of evolution, about where things were going before they were stopped, and the scientific evidence about those trajectories, assembled from the fossil record with increasing precision over the past several decades, makes the question more interesting and more unsettling than it might at first appear. Let us start with what we know. In the final million years before the asteroid impact, a brief moment in geological terms, but long enough to see evolutionary trends clearly, the theropod lineage was undergoing changes in a particular direction. Brains were getting larger relative to body size, a process documented across multiple lineages. Small-bodied, large-brained species were diversifying rapidly. The troodontids, the family to which Troodon belonged, were expanding their geographic range, adapting to a wide variety of environments, and showing morphological signs of continued increase in cognitive capability. The trend was not uniform. Not every dinosaur lineage was heading in this direction. The titanosaur sauropods, already enormous, were not showing significant encephalization. The large ceratopsians were specialized for particular ecological roles that did not demand or reward significant cognitive advancement. But in the small theropods, in the troodontids, in some of the dromaeosaurids, in certain other groups, the arrow was pointing clearly. Now extend that trend 65 million years forward. 65 million years is the time that separates the asteroid impact from the present day. It is also approximately the time that separates the asteroid impact from the first primates, the branch of the mammalian family tree from which humans would eventually emerge. In 65 million years, starting from small shrew-like mammals that survived the impact in burrows and crevices, evolution produced every primate alive today, from mouse lemurs to chimpanzees to us. It produced blue whales, elephants, dolphins, and all the other large-brained, cognitively sophisticated mammals that populate the modern world. What might 65 million years have produced starting from Troodon? We cannot know. Evolution is not linear, not predictable, not deterministic in the way that makes extrapolation possible. The specific path that mammalian intelligence took to reach humans was one of billions of paths that might have been taken. The specific selective pressures, the specific ecological context, the specific genetic mutations that turned out to matter. All of this was contingent, dependent on circumstances that could not have been predicted. But we can note trajectories. We can note that the theropod lineage had, in 90 million years of evolution, produced animals with encephalization quotients comparable to modern birds, and that modern birds, starting from their dinosaur ancestors 66 million years ago, have produced in 66 million years of continued evolution animals with encephalization quotients comparable to some primates. We can note that the trend toward increased encephalization in theropods was, by the end of the Cretaceous, accelerating rather than slowing. We can note that the raw materials, large eyes, grasping hands, social complexity, extended parental care, sophisticated communication, were present in the lineages best positioned to take this path further. And we can note that the universe has, as far as we know, produced high intelligence exactly once on Earth, in our own lineage, starting from those small post-Cretaceous mammals, that this happened in 65 million years of mammalian evolution, and that the theropod dinosaurs had already been on their particular evolutionary journey for 90 million years before the asteroid stopped them. What might they have become? The Canadian paleontologist Dale Russell, in his 1988 speculation, imagined the dinosauroid, a biped with a large domed skull, eyes facing forward, delicate hands capable of precise manipulation, a body plan that convergently approached the human body plan through the independent logic of what intelligence requires. Russell's specific imagining has been criticised on several grounds, some legitimate. There is no particular reason to think that an intelligent dinosaur-descended species would have looked like a scaled and slightly alien version of a human. Intelligence does not require the specific morphological solutions that humans evolved. It can be built on different substrates. But the convergence argument has merit at a deeper level. Many of the structures associated with high intelligence in humans and other primates, large relative brain size, forward-facing eyes with good depth perception, hands capable of precise manipulation, extended juvenile development with substantial parental investment, appear in multiple intelligent lineages on Earth, because they are, in some sense, what intelligence requires or is helped by. They are not accidents. They are functional solutions to the problem of being intelligent in a physical world. Troodon had most of these already. Already in the late Cretaceous, this animal had a larger brain than expected, forward-facing eyes, grasping hands, evidence of parental care, and a social life complex enough to have driven continued selection for cognitive sophistication. The foundation was there. And then there is the most speculative question of all, the one that most paleontologists are reluctant to ask in professional settings, but that comes up inevitably in the informal conversations over dinner after the conference talks are done. If the theropod lineage had continued, if 65 million more years of evolution had pushed it in the direction it was already pointing, might it eventually have produced something capable of what we call technology? Tool use is already documented in modern birds. Crows fashion hooks from stiff leaves to probe for insects and crevices. New Caledonian crows manufacture tools with multiple steps of preparation, showing a kind of proto-technical cognition that is genuinely remarkable. Egyptian vultures use stones as hammers to crack open ostrich eggs. Herons drop bait objects onto water surfaces to attract fish. These are, by any reasonable standard, the beginnings of technology. The intentional modification and use of external objects to extend the body's capabilities. The hands of Troodon were better suited to precise manipulation than the hands of any modern bird. A bird's forelimb is a wing, shaped by 80 million years of evolution for flight. The wing of a crow or raven is not, however ingeniously they use it, a precision manipulator. Troodon's hand was not a wing. It was a hand, with grasping fingers, with the range of motion for precise work, with the eye-hand coordination that binocular vision and an enlarged cerebellum would have supported. If 65 million more years had produced in that hand something like what 65 million years produced in the primate hand, the extraordinary precision grip, the opposition of thumb and forefinger, the ability to make and hold and modify small objects, what might have followed? Stone tools appear in the human record roughly 3 million years ago, roughly 62 million years after the asteroid. They appear not because humans suddenly became intelligent, but because the cognitive threshold for intentional tool production had been crossed. If theropod intelligence had been on a similar trajectory, if 65 million years had built the cognitive threshold in a dinosaur-descended lineage that mammalian evolution built in primates, might stone tools have appeared in the world's record sometime in the distant past? Might there have been a dinosaur civilization? The question sounds absurd, and we should be clear, there is no evidence of any such thing. The fossil record shows no sign of dinosaur technology, no sign of structured settlement or artifact production. The question is purely speculative. but the speculation is grounded in real evolutionary trajectories, and it is worth sitting with, for a moment, in the quiet dark, because what it implies about the universe is something quite profound. Intelligence may not be the unique achievement it seems from where we stand. It may be a direction that evolution finds when given sufficient time and appropriate conditions. Not inevitably, not in every lineage, not always, but as a possibility that emerges again and again wherever the conditions are right. We were not inevitable, but we were also not an accident so improbable that nothing like us could ever have arisen elsewhere. The universe was, in the bodies and the neural tissues of the theropod dinosaurs, already feeling its way towards something like us, before a rock from space wrote a different ending. That is both humbling and, in its own way, comforting. We are part of a story larger than ourselves, a story that was already in progress long before we arrived, a story that, had things gone slightly differently, might have had a different protagonist. But we are the ones who are here. We are the ones who know the story. We are the ones who can ask the question. That is something remarkable. Let it sit with you gently, like a light growing in the far distance. Rest now. Let the question find its place in you, and be still. Let us take a different kind of journey now, not through the evidence, not through the arguments of science and the revision of old assumptions. Let us take a journey into imagination, carefully grounded imagination, informed by everything we have learned tonight, but given permission to breathe and to feel and to dwell in the ancient world rather than merely describe it from outside. Come with me to the late Cretaceous, to the western interior of North America, a place that will one day be Montana, sometime around 75 million years ago. It is evening. The sun has been below the horizon for perhaps an hour. The sky above is the deep, rich blue that precedes true dark, not yet black, still holding the memory of day at the western edge while the stars emerge, one by one, at the zenith. The air is warm, warmer than a Montana evening would be today, because the climate of the late Cretaceous was substantially warmer than our own, and even this far north, winters are mild, and the growing season is long. You're standing at the edge of a river. The river is wide and slow, moving through a floodplain of considerable extent. The vegetation along the banks is lush. Tree ferns and early angiosperms, conifers at the higher ground, a tangle of flowering plants in the undergrowth that is beginning to smell, now that the heat of the day has eased, of something sweet and complex and alive. Somewhere in the thicket an insect is calling. Not the insect sounds you know exactly, but something in the same register, a thin, persistent, high-frequency sound that is part of the audio texture of the late Cretaceous night. And then, from upstream comes something else. It begins as a vibration more than a sound, something you feel in your chest before you hear it clearly. Deep, resonant, pitched somewhere below the range of ordinary sound, but with a quality that somehow reaches directly into the nervous system. It is a hadrosaur call. Coming from a herd somewhere upstream, out of sight around a bend in the river, the sound carries across the water and the open floodplain with remarkable clarity. It is answered. From downstream, a similar sound, different in precise pitch, different in timbre, the acoustic signature of a different individual, perhaps of a different herd or family group. The two calls move across the darkening landscape toward each other, information travelling at the speed of sound through warm Cretaceous air. You do not know, and cannot know, what the calls mean. But you know they mean something. You know that somewhere upstream and somewhere downstream, in the gathering dark, minds are reaching toward each other across the distance with the ancient technology of sound, recognizing, locating, maintaining the web of social relationship that makes survival possible in a world of predators and uncertain resources. After a while, the calls fade. The river continues its quiet work, moving sediment toward the inland sea that covers the middle of this continent, building the floodplain one grain at a time. The stars are fully out now, the Milky Way visible as a pale band across the sky. The same stars, roughly the same positions that shine on you today, though they have moved slightly in the 75 million years since this moment. In the tree line at the edge of the floodplain, there is movement. Small, quick. Not a large animal, but something quick and alert, moving with the confidence of a predator who knows this territory. A troodon, perhaps, or something of that size and type, moving through the darkness with those large night-adapted eyes gathering the faint starlight, reading the landscape in wavelengths you cannot access. It pauses, turns its head toward you, or toward whatever it has sensed, the sound of the river, the small disturbances of a night in the late Cretaceous. The eye catches the starlight for a moment, bright, reflective, alive with the specific quality of awareness that we have been talking about all this night. Something looks at the world. Something is here, in this moment, in this warm darkness, aware of the river and the stars and the specific chemistry of the night air, navigating the ancient world with a mind that is not our mind, but is, in its own way, genuinely a mind, genuinely present, genuinely here. And then it moves on, back into the tree line, back into its own world, following whatever the night has to offer. Small prey, the scent of water, the guidance of a landscape it knows in intimate detail. The river continues, the insects continue their thin, high calling, the stars wheel slowly overhead. And you are left with the sense of something that cannot quite be put into words, but that is perhaps the real point of all the science and all the evidence and all the careful accumulation of facts that we have been moving through tonight. The sense that the ancient world was inhabited, that it was inhabited by beings that were, in various ways and to various degrees, aware that it was not a dark, unconscious backdrop to the eventual drama of human intelligence, but a living world in its own right, full of the experiencing of experience, full of the knowing of the world by minds that knew it differently from how we know it, but knew it nonetheless. Every life that has ever lived on this planet was its own world. Every warm-blooded Cretaceous dinosaur carried in its skull a universe of sensation and memory and social relationship, and something that mattered to it, something that it was oriented toward, something that structured its moment-to-moment existence with the particular quality of aliveness. Those universes are gone. But they were real. They were as real as the universe you're inhabiting right now, as real as the sensations of your own body against whatever holds you, the soft sounds of the night around you, the slow drift of your thoughts towards sleep. The ancient world was real. The dinosaurs were real. Their awareness, whatever its specific character, was real. And we are the inheritors of all of it, not in some mystical sense, but in the literal material sense that we are built from the same atoms, shaped by the same evolutionary forces, situated in the same universe that produced all of those minds. We are continuous with them. We emerged from the same long process. That continuity is worth knowing. It changes how the world feels once you really let it in. The night is full of ancient things. The stars are ancient. The river, if there is one near you, is ancient, carrying in its movement the same physical principles that moved Cretaceous rivers toward Cretaceous seas. The air is full of the descendants of ancient organisms, and you yourself are ancient, in the deep sense, made of matter that has been part of the world for billions of years, shaped by a process that began long before you arrived and will continue long after. Rest in that continuity. Let it hold you, as the ancient world holds all of its moments. The Cretaceous evening, the hadrosaur call, the quick bright eye in the tree line. All of it held permanently in the structure of the universe, in the rocks that preserve the bones, in the light that left those ancient stars and travels still through the dark. Everything that happened is still happening, in the only sense that matters. It was real, and reality is permanent. Sleep now into the ancient night. The world will keep you. There is a fossil site in Colorado called Dinosaur Ridge. It sits along the front range of the Rockies, just west of Denver, and along a particular stretch of exposed rock face you can walk beside a trackway. The preserved footprints of dinosaurs moving across what was, 110 million years ago, the shore of a shallow inland sea. The tracks go in one direction, several different sizes, consistent with a mixed age group, and they go straight, purposefully, directionally straight, along the line of the ancient shore. These animals knew where they were going. This might seem like a simple observation. Animals that move in straight lines are common. Even relatively simple animals, like insects following pheromone trails, move directionally. But the straight-line movement of large vertebrates across complex landscapes is not a simple thing. It implies navigation, the use of internal representations of space, maintained and updated as the animal moves, to guide movement toward a distant goal that may not be directly perceptible. Human navigation depends on maps, either external, physical maps, or internal cognitive maps, spatial representations of the environment built from experience and maintained in memory. When you navigate to a familiar destination without consciously thinking about the route, you're using a cognitive map, a stored spatial representation that your hippocampus and associated brain regions access and use to guide movement. Animals navigate using cognitive maps too. The evidence for this is clearest in species that have been extensively studied, like Clark's nutcrackers and food-caching jays, which demonstrate spatial memory of remarkable fidelity. But cognitive mapping, the ability to build and use internal representations of space, is widespread among vertebrates. Rats show it clearly in maze experiments. Pigeons show it in navigation back to home lofts from release points hundreds of kilometers away. Fish show it in home range navigation. Reptiles show it in return to specific basking and feeding sites. Given this widespread distribution, it is almost certain that non-avian dinosaurs also built and used cognitive maps of their environments. The question is how complex those maps were, and what this tells us about the sophistication of their navigation behavior and the neural machinery underlying it. The scale of some dinosaur movements suggests cognitive maps of considerable extent and detail. Hadrosaur herds in the western interior of North America appear, from the fossil record, to have occupied enormous ranges, seasonal movements that may have covered hundreds of kilometers in each direction. The fossils of a single species appear across a wide geographic area, with patterns consistent with seasonal migration, with different age classes appearing in different areas at different times of year, in ways that suggest organized, structured movement rather than random dispersal. To execute a migration of hundreds of kilometers to a specific destination, an animal needs more than a simple directional compass. It needs to know where it is relative to where it wants to be. It needs to recognize specific landmarks, to anticipate specific terrain features, to adjust its course based on the current position relative to the remembered route. It needs, in short, a cognitive map of the migration corridor, a stored spatial representation detailed enough to guide multi-day or multi-week movement to a specific destination. The learning of migration routes is, in modern migratory animals, a matter of considerable study. In many species, the routes are at least partially learned rather than entirely innate. Young animals follow experienced adults on their first migrations, building their own cognitive maps of the route by following an experienced guide. The specific details of the route, the specific mountain passes, the specific river crossings, the specific stopping points where food and water are reliably available, are acquired through this socially guided experience. This means that the migration route, in socially learning migratory animals, is a cultural artifact. It is information that is passed from experienced individuals to less experienced ones, modified by each generation's experience, accumulated over many generations into the kind of detailed, nuanced knowledge that constitutes the migratory tradition of a population. Human cultures have analogous traditions. Indigenous peoples around the world maintain detailed knowledge of landscape, water sources, seasonal food availability, and routes of travel that has been accumulated and refined over many generations. This knowledge is transmitted through story, through song, through ceremony, and through the direct experience of travel with knowledgeable guides. It is, in a very real sense, the cognitive map of a people, the stored spatial wisdom of generations. The cognitive maps of migratory dinosaurs were not human. They were not encoded in language or story or ceremony. But they may have been transmitted in analogous ways, through the direct experience of migration in the company of experienced adults, with the route encoded in movement and memory rather than words. The complexity of this kind of socially transmitted spatial knowledge is not trivially small. It requires, first, the ability to build detailed spatial representations from experience. It requires the ability to recognize specific landscape features and associate them with specific route information. It requires the ability to transmit this information socially, to learn it from others, and to behave in ways that allow others to learn from you. All of this is well within the range of what we have attributed to the cognitively more sophisticated dinosaur species, and it implies a relationship with the landscape that was, in its way, genuinely sophisticated. Not the abstract map and symbol-based spatial cognition of modern humans, but something that was functionally equivalent in many of the contexts that mattered for survival. The late Cretaceous landscape across which these animals navigated was extraordinary in its extent and variety. The western interior seaway divided North America, creating a coastal corridor along which enormous faunas moved seasonally. Mountain ranges to the west provided vertical relief and distinct ecological zones. River systems draining toward the inland sea provided linear corridors of movement and reliable water. The landscape was structured in ways that rewarded precise spatial knowledge, and the animals that had that knowledge, that carried in their neural tissue the detailed cognitive maps of this landscape, learned through seasons of travel and refined through generations of cultural transmission. Those animals were better equipped to survive than those that did not. The selection pressure for spatial cognition was persistent and strong. This is how intelligence grows. Not through a single dramatic mutation, not through a sudden threshold crossing, but through the persistent pressure of demanding environments on populations of organisms that vary in their cognitive capabilities. Generation by generation, the bar rises. Generation by generation, the cognitive map becomes more detailed, the spatial memory more precise, the ability to transmit spatial information more refined. By the end of the Cretaceous, this process had been running for tens of millions of years in the dinosaur lineage. What it had built in the navigational and spatial cognition of the most sophisticated species, we cannot say with precision, but we can say, with confidence, that it was not nothing. The footprints at Dinosaur Ridge tell a simple story. Animals moved purposefully across a landscape they knew. But simple stories, examined carefully, reveal depths. Those animals knew where they were going because they had been there before, or because someone who had been there before had shown them the way. That knowledge was valuable, costly to acquire and worth maintaining across generations. That is something real. That is intelligence in the service of life. Let the image of the trackway stay with you as you settle deeper into rest. Animals moving across an ancient shore, purposeful and knowing, carrying in their warm bodies the accumulated wisdom of generations, going where they needed to go because they knew where that was. Navigation is one of the oldest forms of intelligence. It is the mind reaching out into space, holding the world at a larger scale than the body occupies. And on those ancient shores, it was already happening. Rest now. Let the world hold you in your particular place, in your particular time, as it has always held the moving, knowing creatures that have crossed its surface. You have seen a dinosaur today. If you live anywhere with birds, and virtually everyone on Earth does, you have encountered a living dinosaur within the last 24 hours. The sparrow at the feeder, the crow on the fence post, the pigeon picking something off the pavement, the hawk circling overhead. These are dinosaurs, not metaphorically, not in a loose evolutionary sense. They are, technically and precisely, avian dinosaurs, the living members of a lineage that extends in unbroken continuity back through the Cretaceous, through the late Jurassic, to the small feathered theropods that were Troodon's contemporaries or ancestors. When we look at birds and see what they are capable of, we are looking at what the dinosaur lineage, given 66 million more years of evolution after the asteroid, has been able to build. And what it has built is extraordinary. Begin with the cognitive achievements of corvids. Crows, ravens, jays, and magpies, the members of the corvid family, are repeatedly documented as among the most cognitively sophisticated animals on the planet. The evidence is not anecdotal. It comes from carefully controlled behavioral experiments, replicated in multiple laboratories, showing cognitive capacities that were, until recently, considered the exclusive domain of primates or humans. New Caledonian crows manufacture tools, not simple tools. They fashion hooks from strips of leaves and twigs that require multiple steps of preparation, with the finished tool shaped specifically for the task of probing for insects in crevices. They have been observed modifying tools that proved inadequate for a task. They have been shown in laboratory experiments to use tools they cannot see in order to obtain tools of the right size to reach food, a demonstration of what researchers call meta-tool use, the use of a tool to obtain a tool. Rooks, another corvid, have been shown to understand the principle of Archimedes' displacement, dropping objects into tubes of water to raise the water level and reach floating food rewards. This is a physical reasoning task that requires understanding causal relationships in the physical world, not just learned associations. Ravens have been documented planning for the future, setting aside a tool they will need the next day, even when doing so means passing up an immediate food reward. Future planning requires the ability to mentally represent a future state of affairs that does not yet exist, which is a cognitively demanding capacity. Perhaps most remarkably, ravens have been shown to have a sophisticated grasp of social dynamics. They track the relationships between individuals other than themselves. They understand that if A dominates B and B dominates C, then A likely dominates C, even if they have never observed A and C interacting directly. They remember the past behavior of specific individuals and adjust their own behavior accordingly. They form strategic coalitions with partners who are useful to them. They engage in reciprocal altruism, helping individuals who have helped them in the past. These capacities are not uniquely avian. Convergent cognitive evolution has produced similar abilities in other lineages that evolved in ecologically similar conditions. Dolphins and orcas show complex social cognition, tool use, and what appears to be cultural transmission of foraging techniques. Elephants demonstrate theory of mind, understanding that others have knowledge they themselves lack, and use this understanding to interpret and predict behavior. Chimpanzees, bonobos, and other great apes show the full range of higher cognitive abilities we associate with near-human intelligence. What is significant about the birds is that they achieve these capacities through a completely different brain architecture than mammals. Mammalian intelligence is associated with the neocortex, the layered outer surface of the brain that is so dramatically expanded in primates. Birds have no neocortex. Their brains are organized completely differently, and yet in the pallium, the avian brain region that appears to be functionally equivalent to the mammalian cortex, though structurally different, evolution has built the equivalent cognitive machinery. This is one of the most important insights in modern neuroscience, that the specific architecture of the mammalian brain is not the only way to build intelligence. The pallium of a crow can produce cognitive feats comparable to those of a primate, using circuitry that looks very different at the cellular level. Intelligence is a functional property, not an architectural one. It can emerge from different physical implementations. This matters for thinking about dinosaurs because it means that the absence of a neocortex in non-avian dinosaurs is not an argument against their cognitive sophistication. Their brains were structured differently from mammalian brains, but differently is not worse, and the functional outcomes, what the brain does, how it processes information, what behavioral capacities it supports, can be sophisticated in many different structural implementations. Modern birds also demonstrate in a living laboratory how quickly the cognitive capabilities that we attribute to high intelligence can evolve when selection pressures favour them. Corvid intelligence appears to have evolved relatively rapidly in evolutionary terms. The ancestral corvids were not the cognitive sophisticates that modern ravens are. The specific conditions of corvid ecology, complex social groups, ecological flexibility, long lives with extended learning periods, appear to have driven rapid evolution of cognitive capability. The same conditions were present, we have argued, in several lineages of non-avian dinosaurs. Social complexity, ecological diversity, extended development, sophisticated communication, the conditions that favour cognitive evolution, and the living birds demonstrate that the dinosaur lineage is capable of producing, when those conditions are in play, animals of remarkable cognitive sophistication. There is something poignant and wonderful about this. The dinosaurs did not go entirely away. They were transformed. Most lineages ended at the extinction, but one lineage did not. The small feathered theropods that survived became the birds, and the birds, in 66 million years of post-Cretaceous evolution, have built something remarkable. When you hear a raven call in the morning, or watch a crow problem solve, or see a parrot learn a new word, you are watching the continuing work of dinosaur evolution. The work that was interrupted in most lineages 66 million years ago is still proceeding in the descendants that made it through, building and elaborating and exploring the space of what a dinosaur mind can do. The ancient world is not entirely gone. It is transformed and continuing. The dinosaur eye that looked out across the Cretaceous landscape is looking out still, from a smaller and more varied body, at a smaller and more complicated world. But it is the same evolutionary lineage, the same ancient heritage, still alive and still growing. When you see a bird, any bird, take a moment with that thought. That creature is connected in unbroken lineage to the world we have been exploring tonight. It carries in its brain and bones and the specific structure of its awareness something that has been developing and refining since the Triassic, something ancient and continuous, and in its own way extraordinary. We are surrounded by dinosaurs, and the dinosaurs, it turns out, are more than we thought. Let that quiet recognition settle into you as you rest. The night around you is inhabited by small warm-blooded descendants of the ancient rulers, sleeping in their own ways in their own places, by the continuing life of a lineage that has been exploring the possibilities of awareness for longer than we can easily imagine. Sleep gently into the knowledge of this vast and continuing company. You are not alone in the night. You are surrounded by the living history of a planet that has been busy, all this time, building minds. There is a bone, held in a museum drawer in a collection that few members of the public ever visit, that tells a story of almost unbearable poignancy. It is a dinosaur bone, a theropod, a moderately sized carnivore from the late Cretaceous, and it shows evidence of a healed fracture. Not a clean-healed fracture of the kind that results from a crack knitting back together in an animal that has simply rested the bone. This fracture shows the callus formation and remodeling consistent with a bone that was seriously broken and then allowed to heal over a period of many months. The animal survived. A large theropod with a severely fractured limb bone in the late Cretaceous should not have survived. It could not have hunted effectively. It could not have moved at speed. It would have been unable to compete for resources in the way that a healthy animal could. The ecological logic says it should have died quickly, from starvation, from predation, from the myriad threats that a vulnerable animal in a world of predators would have faced, and yet it lived, long enough for that bone to heal completely. How? The most conservative answer is that the animal was simply lucky, that it found sufficient scavenged food and sufficient shelter to survive the healing period without assistance from other animals. This is possible. Animals have survived serious injuries without social support under favourable circumstances, but there is another possibility, one that the fossil record cannot definitively confirm or refute, but that is, given everything else we have been discussing about dinosaur social life and cognitive sophistication, at least worth considering. What if the animal was helped? Helping injured or sick group members, providing food, offering protection, tolerating the presence of a non-contributing individual during a period of vulnerability, is a behaviour documented in several cognitively sophisticated modern animals. Elephants support injured herd members, slowing their pace to match the injured animal, staying with individuals who cannot keep up. Wolves in a pack have been observed bringing food to pack members recovering from injury. Dolphins support individuals who are having difficulty swimming, physically propping them up to allow them to breathe. Chimpanzees have been documented grooming and caring for sick or injured group members, and have been observed what appear to be grief responses to the deaths of close associates. In each of these cases, the helping behaviour requires several things. It requires the ability to recognise that another individual is in a different state from normal, injured, sick, vulnerable. It requires the ability to relate that altered state to the individual's identity, to maintain a relationship-specific response rather than a generic one. And it requires, in some sense, the motivation to expend resources and effort on behalf of another individual from whom no immediate reciprocal return is likely. These requirements add up to a fairly demanding cognitive and motivational profile. They require social cognition of considerable sophistication and motivational systems that extend beyond narrow self-interest to encompass something like concern for others. In the biological literature, this is often discussed in terms of empathy, the capacity to represent the internal states of others and to respond to those representations with appropriately tuned behavioural responses. Empathy, in this functional sense, is not uniquely human. Functional empathy, the capacity to respond to the distress or need of others in ways that reduce that distress or need, has been documented in rodents, in birds, in primates, and in other social vertebrates. If the hadrosaur herds and the theropod social groups that we have been describing had the cognitive machinery for individual recognition, for social bonding, for complex communication, and the evidence suggests they did, then they also had, potentially, the cognitive machinery for something like functional empathy, for something like caring whether specific other individuals were doing well or badly. This is speculative. The fossil record cannot tell us whether dinosaurs ever supported injured group members, and the single healed fracture bone that prompted this discussion could have resulted from fortunate circumstances rather than social support. The argument is inferential, not evidential. But consider the trajectory. Modern birds, animals derived from theropod dinosaurs, show clear evidence of functional empathy. Corvids have been documented comforting distressed individuals. Geese have been observed staying with injured mates, calling to them, waiting beside them even at the cost of falling behind the flock. Parrots form pair bonds that, when broken, produce what appear to be genuine grief responses. The emotional and social lives of birds are far richer than the old stereotype of bird-brained automatons allowed. If modern birds, derived from small theropod dinosaurs, have these capacities, and if the evolutionary preconditions for these capacities were present in the social structures of their theropod ancestors, as we have argued they were, then the question of whether injured or sick dinosaurs receive something like care from their social groups is a genuine question, not a fanciful one. The healed bone sits in its museum drawer, silent about the circumstances of its healing. But it whispers something. It says that this animal survived against the odds, and that something, luck or shelter, or perhaps the proximity and tolerance of others who kept it fed and kept the predators at bay, allowed it to return to health. We will probably never know which it was. But the question is worth asking, because if the answer is that social support played a role, if theropods or hadrosaurs or ceratopsians sometimes help their injured, then we are looking at something that has a very human feel to it, across 66 million years of distance. We care for our wounded. We always have. It is one of the things that distinguishes human social groups from purely competitive aggregations. We invest in the survival of individuals who cannot contribute to the group's immediate welfare, because we recognize them, because we are bound to them, because their well-being matters to us in a way that transcends simple calculation. This capacity, empathy, compassion, the extension of care beyond the self, is not uniquely human. It evolved. It evolved because it was adaptive, because social bonds that included mutual aid and care for the vulnerable were more durable and more successful than purely competitive ones. It evolved because the cognitive machinery to recognize individuals, maintain relationships, and respond to the needs of others was built into organisms whose social lives demanded it. It may have begun evolving in some form very long ago, in the warm-blooded, socially complex animals of the Cretaceous who built their nesting colonies and called to each other across the ancient floodplains and perhaps, in moments of vulnerability and need, stayed close to those they knew. That is not sentiment. That is the beginning of something that has become, in us, one of the things we value most about ourselves. Rest with that thought. The capacity for care is old. It grew from old roots, in old worlds, in animals that we are only beginning to understand. The night is full of old things, full of old kindnesses and old bonds and the deep persistent inclination of social creatures to stay close to those they know. You are the current expression of something ancient and good. Rest into that. Let sleep come now, soft and gradual and complete. Let it take you to whatever country it takes you to, deep and dark and restoring. The world will be here when you return to it. The science will have moved forward probably. There will be new fossils, new analyses, new revisions of old certainties. But the deep wonder at the heart of all of it, the astonishment that the world is so old and so complex and so alive, that will remain. That is always there, under everything, reliable as gravity. Dream of ancient eyes and ancient skies. Good night. Where in the world are you watching from? Let us know in the comments, and don't forget to subscribe if you want to see more videos like this.